In the beginning, there was only silence. A silence so vast, so overwhelming, that even the faintest whisper of starlight felt like a message. The universe is a theater of motion, where everything travels, drifts, collides, and fades. Stars are born, galaxies expand, and worlds we cannot yet imagine orbit suns we will never see. But sometimes, something unusual crosses our skies, something that doesn't belong. This is the story of one such arrival, a rare traveler known to astronomers as 3I/ATLS, an interstellar object, neither native to our solar system nor bound by its gravity. A piece of some other star's story, passing briefly through ours. And yet, as its trajectory carried it across the watchful eyes of our telescopes, a question arose. Was 3I/ATLS simply a visitor, or was it something more? A kind of message, whispered across the dark ocean of space. To understand, we must first recognize the stage on which this story unfolds. Our solar system is a family of worlds orbiting a single, middle-aged star. For billions of years, it has remained relatively undisturbed. Comets and asteroids wander its outskirts, but most are bound to the sun, prisoners of its gravity. Objects from outside are extraordinarily rare. For most of human history, none had ever been confirmed. We looked up at the stars, but believed that whatever crossed our sky was born here, in our system, under the watch of our sun. That belief changed only recently. First came Oumuamua, a strange and elongated body that defied easy explanation. Then came Borisov, a comet unmistakably foreign in origin. And now 3I/ATLS, our third confirmed interstellar visitor, each one mysterious, each one a messenger from beyond. Why do their arrival matter? It is not only their rarity, it is what they represent. They are cosmic fragments of stories we cannot otherwise hear. Messages in bottles, cast adrift on currents of starlight, traveling across unimaginable distances to wash upon the shores of our awareness. 3I/ATLS does not have the same fame as its predecessors. It lacks the dramatic acceleration of Oumuamua, which inspired debates about alien technology. It does not glow with the brilliant tail of Borisov, a comet from another sun. Atlas is quieter, subtler, easier to overlook, and yet its very existence is profound. It was discovered by the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short, a survey designed to protect us by spotting potential cosmic hazards. At first, it seemed like just another dim speck among the countless points of light the survey captures every night. But closer examination revealed something unusual. Its orbit was not bound to our sun. Its path was hyperbolic, meaning it did not loop back around like a comet or asteroid native to our system. Instead, it came from elsewhere and would one day return to the endless dark, never to be seen again. That single fact placed it in one of the rarest categories of all, an interstellar object, the third ever detected by humanity. But with that recognition came new questions. Where had it come from? What forces had cast it out of its home? What ancient star system had once claimed it as part of its world? No one can say for certain. Interstellar objects like 3I/ATLS are thought to be fragments, shards of planets or comets ejected by violent collisions or the chaotic births of other star systems. They may be icy relics preserved for billions of years, or rocky remnants blasted free when suns and planets first formed. But perhaps they are something stranger. Some scientists argue that not all such visitors must be natural. Some could be engineered, probes, instruments, relics of civilizations too distant or too ancient for us to imagine. The possibility, however remote, lingers in the minds of those who study them. This is why they fascinate us, because each one is a messenger of the unknown. They are physical evidence that the galaxy is alive with movement, filled with fragments of places we cannot yet see. By studying them, we catch glimpses of alien chemistry, alien history, perhaps even alien intent. In a way, every interstellar object is a kind of message, not necessarily a deliberate transmission, but a signal all the same. Consider a seashell on a beach. It was not left for you. It does not carry instructions, and yet it tells a story of the ocean that shaped it, of the life that once carried it, of the forces of time and tide. So it is with 3I/ATLS. Its path across our sky may not have been intentional, but it carries within it the fingerprints of a world we will never visit. Its composition, its structure, its movement, all of these are the words of its message. They speak of a wider galaxy, a living cosmos in which our solar system is but a small corner. And yet we cannot ignore another possibility. What if some of these visitors are not simply natural? What if their arrival is not coincidence? When Oumuamua passed through, its odd shape and unexplained acceleration sparked intense debate. Could it have been a fragment of alien technology, a probe, or a relic? The scientific community is divided, but the question remains open. 3I/ATLS does not display the same anomalies. It seems, by all appearances, more ordinary. But its very ordinarity invites a deeper question. If interstellar visitors are appearing this frequently, are they truly rare? Or are they simply common, and now we are only beginning to notice them? If the galaxy is full of such wanderers, then perhaps our skies are alive with signals we have not yet learned to read. So we return to the question, is 3I/ATLS a visitor or a message? To call it a visitor is to accept the simplest truth. It is an object from beyond, crossing our domain, indifferent to our existence. It arrives, it departs, and it leaves us to wonder. But to call it a message is to recognize its deeper significance. It is to admit that its presence matters, not just scientifically, but philosophically. That by studying it, by reflecting upon it, we are participating in a larger conversation, one that transcends language, culture, even species. Perhaps the real importance of 3I/ATLS lies not in what it is, but in what it awakens within us. The urge to ask questions, the desire to listen for whispers in the silence of space, the recognition that the universe is larger, older, and more complex than we can comprehend. Our solar system is not an island. The stars are not distant decorations, but neighbors in a galactic community. And objects like 3I/ATLS are the bridges, fragile, fleeting bridges that remind us of this truth. They tell us that the galaxy is connected, that what happens in one system can echo across the stars to another, that the void is not empty, but full of travelers, each carrying stories from long before we were here and long after we are gone. And so 3I/ATLS passes across our sky, quiet, unassuming, easy to miss. But in its silence, it poses a question that will not leave us. Are we simply observers of a passing stranger? Or have we just received a message written in the language of the stars?
3I, Atlas, a name that sounds like a cipher,
stripped of poetry, wrapped in the cold precision of scientific notation. Yet behind this technical label lies a story of extraordinary significance, one that links human curiosity with the deep motions of the galaxy itself. To understand the name, we must first unravel its parts. The 3I signals its place in a very short lineage. The I stands for interstellar, a designation reserved for the rare class of objects that come from beyond the sun's domain. The number 3 reveals that it is only the third of its kind ever to be confirmed. Before it, there were just two others, Oumuamua in 2017 and Borisov in 2019. That is all. Out of the countless comets and asteroids humanity has cataloged, 3 have carried this mark. The second half of its name, Atlas, carries a different weight. It honors the system that discovered it, the Asteroid Terrestrial Impact Last Alert System, a survey program designed not to search for cosmic mysteries, but for threats. Atlas is humanity's early warning line, a set of telescopes in Hawaii that sweep the skies every night, scanning for any object on a path that might one day collide with Earth. It is a sentinel, watching, recording, and alerting us to dangers that move silently against the backdrop of the stars. On one such night in 2019, Atlas detected something new. At first, it appeared to be nothing remarkable, just a faint, moving point of light, shifting slightly against the canvas of stars. The system flagged it, as it does countless others, and passed it to astronomers for further study. But soon patterns began to emerge. When scientists calculated its orbit, they found something extraordinary. Unlike the vast majority of objects in our skies, this one was not bound to the sun. Its path was hyperbolic, an open curve, not a closed loop. In simple terms, it meant the object was traveling too fast to be held by the sun's gravity. It had not been born here, and it would not stay. It was a drifter, a wanderer from another star system, crossing ours only briefly before continuing its long journey through interstellar space. This realization changed everything. What seemed at first like another comet was revealed to be a true interstellar visitor. Astronomers gave it its official designation, 3I Atlas. The naming itself is worth pausing on, because names carry meaning. In astronomy, the system of naming interstellar objects is still new, forged only in the past decade. The first, Oumuamua, was given a name rooted in Hawaiian language, a messenger from afar arriving first to honor its place of discovery and its unprecedented nature. The second, Borisov, bore the name of the amateur astronomer who first detected it. By the time of the third, conventions were still fluid, but the designation had crystallized: number, class, and discoverer. Thus, 3I Atlas. To some, the name may feel clinical, more a serial number than a story. But in its sparseness, it contains both humility and recognition. It marks 3I Atlas as one of the rarest categories of objects ever known, and it ties its discovery to the instruments and people who made it visible to us. But to truly grasp the importance of 3I Atlas, one must step back and appreciate the odds. For billions of years, objects like this have surely passed through the solar system. Ejected by the gravitational chaos of their birth systems, they wander the galaxy as interstellar nomads. Some may have crossed our path countless times before, but we never noticed them. Why? Because until very recently, we lacked the eyes to see. Our telescopes were too narrow, our surveys too slow, our ability to scan the heavens too limited. It is only in the past 2 decades, with wide-field surveys like Pan-STARRS, Catalina, and Atlas itself, that humanity has gained the capacity to notice such faint, fast-moving visitors. In other words, these objects have always been there, but only now are we able to catch them in the act. Think of that for a moment. For all of human history, thousands of years of staring at the stars, charting their movements, weaving myths and science alike, we never saw one. And now, within just a few years, 3 have appeared in our records. What changed was not the galaxy, but us, our technology, our vigilance, our expanding vision. And so 3I Atlas is not just another dot in the sky. It is a marker of a turning point. It tells us that humanity is entering a new era in which we can finally detect the messengers that have been slipping past us for eons. It is a sign that our tools are catching up with the reality of the universe around us. When astronomers first announced the discovery of 3I Atlas, it did not ignite headlines in the same way that Oumuamua had done. There were no debates about alien probes, no frenzy of speculation about strange shapes or impossible accelerations. Atlas appeared to be more ordinary, less dramatic. But to the scientific community, its importance was clear. It confirmed that Oumuamua and Borisov were not flukes. Interstellar visitors were real, and they might be more common than anyone had dared to hope. In that sense, 3I Atlas is a quiet revolution. Its discovery expanded a lineage that had only just begun. First, 1 interstellar object, then 2, now 3. Each one adds weight to the idea that our solar system is not an isolated island, but part of a dynamic, interconnected galaxy where matter flows across the spaces between stars. And while the name 3I Atlas may sound impersonal, it anchors the object in human memory. 3I tells us where it fits in the sequence, a reminder that it belongs to a family, however small, of rare wanderers. And Atlas ties it to the instruments that spotted it, the watchful system that made its presence known. Without those telescopes, it would have remained invisible, a ghost passing unseen through our skies. It is humbling to realize how much lies beyond our perception waiting for us to notice. For every 3I Atlas that we catch, there may be hundreds, thousands more, slipping by unnoticed, carrying within them the stories of other suns, other worlds, other beginnings. Each one is a clue to the broader architecture of the galaxy. Each one is a piece of a puzzle we are only just beginning to solve. So what is 3I Atlas? It is a visitor, yes, a wanderer from beyond. But it is also a symbol of our growing ability to see beyond our borders, a symbol of the hidden traffic of the cosmos, the constant exchange of matter between distant systems, a symbol of connection, of belonging to a galaxy that is not empty, but alive with motion. Its name may be technical, but its story is anything but. 3I Atlas is a reminder that even in the cold language of catalog numbers, there are tales of wonder. The tale of a fragment of another star system crossing our own, and of a species, us, finally able to notice. And perhaps, hidden in that name, there is an unspoken message, that the universe has been whispering to us all along, and only now are we learning to listen.
3I Atlas. A name that sounds like a cipher, stripped of poetry, wrapped in the cold precision of scientific notation. Yet behind this technical label lies a story of extraordinary significance, one that links human curiosity with the deep motions of the galaxy itself. To understand the name, we must first unravel its parts. The 3I signals its place in a very short lineage. The I stands for interstellar, a designation reserved for the rare class of objects that come from beyond the sun's domain. The number 3 reveals that it is only the third of its kind ever to be confirmed. Before it, there were just 2 others, Oumuamua in 2017 and Borisov in 2019. That is all. Out of the countless comets and asteroids humanity has cataloged, 3 have carried this mark. The second half of its name, Atlas, carries a different weight. It honors the system that discovered it. The Asteroid Terrestrial Impact Last Alert System, a survey program designed not to search for cosmic mysteries, but for threats. Atlas is humanity's early warning line, a set of telescopes in Hawaii that sweep the skies every night, scanning for any object on a path that might one day collide with Earth. It is a sentinel, watching, recording, and alerting us to dangers that move silently against the backdrop of the stars. On one such night in 2019, Atlas detected something new. At first, it appeared to be nothing remarkable, just a faint, moving point of light, shifting slightly against the canvas of stars. The system flagged it, as it does countless others, and passed it to astronomers for further study. But soon, patterns began to emerge. When scientists calculated its orbit, they found something extraordinary. Unlike the vast majority of objects in our skies, this one was not bound to the sun. Its path was hyperbolic, an open curve, not a closed loop. In simple terms, it meant the object was traveling too fast to be held by the sun's gravity. It had not been born here, and it would not stay. It was a drifter, a wanderer from another star system, crossing ours only briefly before continuing its long journey through interstellar space. This realization changed everything. What seemed at first like another comet was revealed to be a true interstellar visitor. Astronomers gave it its official designation, 3I Atlas. The naming itself is worth pausing on because names carry meaning. In astronomy, the system of naming interstellar objects is still new, forged only in the past decade. The first, Oumuamua, was given a name rooted in Hawaiian language, a messenger from afar arriving first, to honor its place of discovery and its unprecedented nature. The second, Borisov, bore the name of the amateur astronomer who first detected it. By the time of the third, conventions were still fluid, but the designation had crystallized: number, class, and discoverer. Thus, 3I Atlas. To some, the name may feel clinical, more a serial number than a story, but in its sparseness, it contains both humility and recognition. It marks 3I Atlas as one of the rarest categories of objects ever known, and it ties its discovery to the instruments and people who made it visible to us. But to truly grasp the importance of 3I Atlas, one must step back and appreciate the odds. For billions of years, objects like this have surely passed through the solar system. Ejected by the gravitational chaos of their birth systems, they wander the galaxy as interstellar nomads. Some may have crossed our path countless times before, but we never noticed them. Why? Because until very recently, we lacked the eyes to see. Our telescopes were too narrow, our surveys too slow, our ability to scan the heavens too limited. It is only in the past 2 decades, with wide-field surveys like Pan-STARRS, Catalina, and Atlas itself, that humanity has gained the capacity to notice such faint, fast-moving visitors. In other words, these objects have always been there, but only now are we able to catch them in the act. Think of that for a moment. For all of human history, thousands of years of staring at the stars, charting their movements, weaving myths and science alike, we never saw one. And now, within just a few years, 3 have appeared in our records. What changed was not the galaxy, but us, our technology, our vigilance, our expanding vision. And so, 3I Atlas is not just another dot in the sky, it is a marker of a turning point. It tells us that humanity is entering a new era, one in which we can finally detect the messengers that have been slipping past us for eons. It is a sign that our tools are catching up with the reality of the universe around us. When astronomers first announced the discovery of 3I Atlas, it did not ignite headlines in the same way that Oumuamua had. There were no debates about alien probes, no frenzy of speculation about strange shapes or impossible accelerations. Atlas appeared to be more ordinary, less dramatic, but to the scientific community, its importance was clear. It confirmed that Oumuamua and Borisov were not flukes. Interstellar visitors were real, and they might be more common than anyone had dared to hope. In that sense, 3I Atlas is a quiet revolution. Its discovery expanded a lineage that had only just begun. First, one interstellar object, then two, now three. Each one adds weight to the idea that our solar system is not an isolated island, but part of a dynamic, interconnected galaxy where matter flows across the spaces between stars. And while the name 3I Atlas may sound impersonal, it anchors the object in human memory. 3I tells us where it fits in the sequence, a reminder that it belongs to a family, however small, of rare wanderers. Atlas ties it to the instruments that spotted it, the watchful system that made its presence known. Without those telescopes, it would have remained invisible, a ghost passing unseen through our skies. It is humbling to realize how much lies beyond our perception, waiting for us to notice. For every 3I Atlas that we catch, there may be hundreds, thousands more, slipping by unnoticed, carrying within them the stories of other suns, other worlds, other beginnings. Each one is a clue to the broader architecture of the galaxy. Each one is a piece of a puzzle we are only just beginning to solve. So what is 3I Atlas? It is a visitor, yes, a wanderer from beyond, but it is also a symbol of our growing ability to see beyond our borders, a symbol of the hidden traffic of the cosmos, the constant exchange of matter between distant systems, a symbol of connection, of belonging to a galaxy that is not empty, but alive with motion. Its name may be technical, but its story is anything but. 3I Atlas is a reminder that even in the cold language of catalog numbers, there are tales of wonder. The tale of a fragment of another star system crossing our own, and of a species, us, finally able to notice. And perhaps hidden in that name, there is an unspoken message that the universe has been whispering to us all along, and only now are we learning to listen.
Every story of discovery begins with a single moment, a point when the unknown first comes into focus. For 3I Atlas, that moment occurred in the year 2019, when a faint smudge of light was noticed in the endless sweep of the heavens. Its discovery did not arrive with fanfare. There was no grand announcement, no immediate recognition that humanity had witnessed something extraordinary. Instead, it began in quiet routine, with instruments doing what they were built to do: scanning, recording, and cataloging the night sky. The object was first detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a project operated by the University of Hawaii. The program's purpose was not to uncover mysteries of galactic travel, but to serve as an early warning system for Earth. Its telescopes were designed to detect hazardous near-Earth objects, asteroids and comets whose paths might someday intersect with our planet. ATLAS is composed of a network of small but powerful telescopes, positioned strategically in Hawaii and later expanded to other sites. Each night, these automated eyes sweep wide sections of the sky, capturing image after image. The data is then processed by computers programmed to spot moving points of light, objects that shift position relative to the fixed background of stars. On one of these routine nights, the telescopes captured such a point. To the untrained eye, it would have been indistinguishable from countless others. Just a tiny dot, faint and unremarkable. But as the automated system tracked it across successive images, its motion revealed that it was not a star, not a planet, but something closer, something moving fast. Astronomers initially cataloged it as another minor body, a cometary fragment or small asteroid. Dozens of such objects are logged each month by surveys like Atlas. At first, there was no reason to suspect anything unusual. But then came the calculations. Orbit determination is one of the quiet marvels of modern astronomy. By measuring an object's position across multiple nights and comparing its motion against the pull of gravity, researchers can chart its trajectory with astonishing precision. These calculations are routine, but they are also revelatory. They turn faint streaks of light into stories of movement, stories that stretch backward into the past and forward into the future. When the orbit of this faint Atlas object was computed, astronomers realized something astonishing. Its path was not an ellipse, the closed loop that defines asteroids and comets bound to the Sun. Instead, it was hyperbolic, an open curve. This meant it was moving too fast to ever be captured by the Sun's gravity. It was not from here. It had entered from interstellar space and was destined to leave again. This was the moment when 3I Atlas revealed itself for what it truly was, not a local body, but a galactic visitor. The recognition spread quickly through the astronomical community. Data was shared, refined, and verified. Observatories across the world turned their instruments toward the object, seeking to measure its brightness, its spectrum, its behavior. In the language of science, it transitioned from being a catalog entry to a subject of urgent interest. The official naming soon followed. It was designated 3I Atlas, the third known interstellar object discovered by the Atlas system. The designation itself carries weight. The 3I marks its place in a history that, until 2017, did not exist at all. The first interstellar object, Oumuamua, had shocked the scientific world. The second, Borisov, confirmed that interstellar comets were real. And now the third, Atlas, cemented the idea that such visitors are not isolated curiosities, but part of a broader cosmic reality. But behind the name lies a team of people and machines. The Atlas project is led by astronomers at the University of Hawaii's Institute for Astronomy, with support from NASA's Planetary Defense Coordination Office. Its telescopes, modest in size compared to the great observatories of the world, nonetheless are highly efficient survey instruments. Their power lies not in grandeur, but in persistence. They watch tirelessly, night after night, sweeping the skies for anything that moves. The detection of 3I Atlas was not a stroke of luck, but the result of years of preparation and design. The telescope's wide fields of view, the automated detection algorithms, the networks of follow-up observations, all of these pieces had to be in place for this faint visitor to be noticed. Once the discovery was confirmed, international cooperation took over. The Minor Planet Center, the global clearinghouse for small body observations, disseminated the data to astronomers worldwide. Observers from Europe, Asia, and the Americas contributed follow-up measurements, refining its orbit and confirming its interstellar trajectory. This collaborative chain of events is the quiet heartbeat of modern astronomy. No single person discovered 3I Atlas in the romantic sense. Instead, it was the product of instruments, software, and a global network of scientists working together. The discovery timeline is not marked by dramatic revelations, but by steady accumulation of evidence. Each observation layering upon the last, each calculation sharpening the truth. The realization that 3I Atlas was interstellar unfolded in stages. First came the initial detection, logged without fanfare. Then the orbital calculations, which hinted at its hyperbolic path. Then the confirmations from other observatories, strengthening the case. Finally, the formal designation, which sealed its place in history. What began as a faint dot of light became, step by step, a cosmic messenger, carrying with it the story of another star system. The telescopes involved may seem modest compared to giants like Keck or Hubble, but their role was pivotal. The Atlas system, with its ability to scan the entire visible sky every 2 nights, is designed to catch fleeting objects. Its mission is planetary defense, but in this case, its vigilance extended humanity's reach into interstellar space. By catching 3I Atlas, Atlas proved that the tools we build for one purpose can often serve another, revealing wonders we did not anticipate. It is worth remembering how ephemeral such discoveries are. Objects like 3I Atlas move quickly. By the time its nature was understood, it was already speeding away, growing fainter with each passing night. Astronomers had only a narrow window in which to observe it. That they succeeded at all is a testament to the global coordination of modern science. The timeline of discovery also highlights how new this field is. Before Oumuamua, there was no formal system for naming interstellar objects. No guidelines existed for how to classify them. It was only after that first shock that the nomenclature of I was introduced. Thus, when Atlas appeared, it slotted neatly into a structure that had only just been created. In a sense, the discovery of 3I Atlas is not just about the object itself, but about the rapid evolution of our ability to recognize and categorize such phenomena. Every piece of data collected during its brief passage now holds value. Its brightness, its faint tail-like activity, its subtle shifts in trajectory, all are clues. Astronomers will analyze them for years, comparing them to what we learned from Oumuamua and Borisov. Each visitor adds a layer to our understanding, expanding the story of how interstellar objects behave. So the timeline of 3I Atlas is more than a sequence of dates. It is a narrative of attention, of learning, of recognition. It shows how the machinery of science, telescopes, algorithms, databases, collaborations, can turn the faintest signal into a revelation. It is a story of how the ordinary becomes extraordinary, how a dot of light becomes a messenger from the stars. In the cold arithmetic of discovery, 3I Atlas was one more entry in a
Imagine a grain of dust carried by a cosmic wind, a fragment torn from a faraway world, set adrift into the immeasurable night. This is the story of 3I Atlas, not just its fleeting passage through our skies, but its long, incomprehensible journey across the galaxy. To reconstruct its path is to trace a thread across space and time, a thread that may stretch for millions of years, perhaps even billions. For interstellar objects like Atlas are not travelers in any deliberate sense. They are castaways, fragments ejected from their home systems by forces so powerful they overcame the gravity of their own stars. Once freed, they become nomads, roaming the galaxy in silence. Astronomers, working with the brief observations of Atlas during its pass through the solar system, were able to piece together part of its trajectory. They found that it approached the solar system on a hyperbolic orbit, arriving from the direction of the constellation Ursa Major, the Great Bear, the familiar northern pattern that holds the Big Dipper. From our perspective, that was its origin point. But this is only a projection. The galaxy itself is in motion, and stars shift positions over immense spans of time. What we call Ursa Major today may not have existed in the same configuration when Atlas began its journey. Still, the constellation gave astronomers a point of reference. Atlas entered our cosmic neighborhood from this direction at a speed estimated to be around 30 kilometers per second relative to the Sun, about 67,000 miles per hour. It was moving far too quickly to have originated within our solar system, far too swiftly to ever be recaptured. It came in on a one-way path, destined to pass once and never return. 30 kilometers per second may sound impossibly fast, yet in cosmic terms, it is unremarkable. Stars themselves orbit the center of the Milky Way at hundreds of kilometers per second. Interstellar objects stripped from their home systems inherit these stellar motions. They drift at speeds consistent with the gravitational choreography of the galaxy, their paths shaped by the slow whirl of stars around the galactic core. This means Atlas may have been wandering for eons. Some estimates suggest such objects could drift for hundreds of millions of years before encountering another star system. Imagine the distances it must have crossed, the uncountable number of silent voids and glowing suns it has passed in the dark. As it approached our Sun, Atlas followed the geometry dictated by gravity. Its path bent inward, curving gently as it entered the solar system's outer reaches. At its closest approach, or perihelion, it swept past the Sun at a distance of about 0.25 astronomical units, roughly 37 million kilometers, closer than Mercury, closer than any ordinary comet would dare to, yet it did not burn brightly. Instead, its faint, unstable glow hinted at a fragile structure, a body already weakening under the Sun's relentless heat. Unlike 2I Borisov, which blazed with cometary activity, Atlas seemed fragile, perhaps even fragmentary. Some astronomers believe it may have broken apart as it neared the Sun, its nucleus crumbling into smaller pieces. If so, it was a reminder of the fragility of such travelers. After millions of years adrift, the stress of one brief solar encounter may have been enough to destroy it. From Earth's perspective, the object's passage was fleeting. It entered the inner solar system, made its arc around the Sun, and then sped outward again, fading as it went. Observers had only a short window of weeks to study it before it grew too faint for even the largest telescopes. Soon it was gone, lost again to the galaxy, leaving only data in its wake. But what of its origin? Where truly did it come from? This is perhaps the most tantalizing question of all, and also the most difficult to answer. To trace an interstellar object backward is to wrestle with uncertainty. Its trajectory can be plotted relative to the Sun, yes, but the Sun itself is not still. It is orbiting the center of the Milky Way, as are all the stars around it. Over millions of years, stellar motions blur, shifting the frame of reference. Even a tiny error in calculation magnifies over cosmic time. Still, astronomers have tried. By modeling the object's inbound trajectory and comparing it with the motions of nearby stars, researchers attempt to identify potential home systems. Some have suggested that Atlas may have originated in the region of Ursa Major, but not from any specific star we can name with certainty. Others argue that its path is consistent with ejection from a binary star system, where gravitational interactions can sling objects outward with tremendous velocity. The truth is that Atlas could have come from almost anywhere. It might have once circled a small, faint red dwarf star, orbiting silently in the cold outskirts of its system. It might have been part of a forming planetary disk, only to be hurled away during the chaotic birth of new worlds. It could even be debris from a planetary collision flung into interstellar space by a cataclysm we will never see. What we know is this. At some point in the deep past, Atlas was bound to another star, and then it wasn't. Something, gravity, collision, or disruption, cast it free. And once free, it became a wanderer, doomed or perhaps blessed to drift between stars, never again belonging to one. Its speed tells us something else. At 30 kilometers per second relative to the Sun, Atlas is fast, but not unusually so for interstellar objects. It suggests that its ejection was not extreme. Perhaps it was nudged outward slowly, given just enough energy to escape. This makes it a typical fragment of galactic traffic, part of the unseen river of debris that likely flows between star systems constantly. The sheer thought of its journey is humbling. Picture Atlas in the void, unlit and unseen, moving across the black gulfs where stars are pinpoints of light, separated by years of darkness. Imagine it passing silently by other systems, slipping unnoticed through the outer realms of alien suns. To those systems, it was nothing. No one saw it. No one named it. Only when it reached us, only when our telescopes caught its faint light, did it become a story. And yet, despite the mystery, its path through our skies was predictable. The laws of gravity are universal, and they allowed astronomers to chart its course both backward and forward. We know where it came from in the relative sense, and we know where it is going. After leaving the inner solar system, Atlas will continue outward, climbing back into the dark. It will cross the orbit of Neptune, then drift through the Kuiper Belt, then beyond the Oort cloud, and after that, after tens of thousands of years, it will re-enter the interstellar void, another starless traveler on a starless path. For humanity, the encounter was brief. For Atlas, it was just one moment in an unimaginably long voyage. The journey of 3I Atlas, then, is not just its arc through the solar system. It is a story written across galactic time, a fragment torn free of its birthplace, set adrift into a sea of stars, crossing our path for a heartbeat, and then vanishing again into the abyss. We may never know where it began. We may never know what system once warmed it with light or what planets once circled near it. But in tracing its path, in calculating its speed and direction, we glimpse the motion of the galaxy itself. We see how stars are not islands but participants in a grand, swirling dance, shedding fragments that wander and weave between them. And in that wandering, in that long and lonely voyage, we find meaning. For Atlas is not just a fragment of rock or ice. It is evidence that the galaxy is connected, that the boundaries between star systems are porous, that the material of one world can cross into another. It is a reminder that even across the emptiest distances, there is motion, there is exchange, there is story. This was the journey of 3I Atlas, a voyage through the Milky Way, a passage into our skies, and a departure back into the endless dark.
The word visitor carries a certain weight. It implies an arrival from outside, a crossing of thresholds, a presence that does not belong to the familiar order of things. It suggests impermanence, that the one who comes will not stay. And it conveys something more subtle, too, a sense of relationship. A visitor is not a stranger wandering without notice. A visitor is someone who enters a place and is seen. When astronomers describe 3I ATLS as a visitor, they're choosing a word that resonates with all of these meanings. It is not merely a comet or asteroid, not simply another stone in the endless cascade of bodies circling our sun. It is something other, something from beyond. To understand why the term matters, we must first look at what ordinary objects in our solar system are. For most of human history, everything we observed moving through our skies, planets, moons, asteroids, comets, shared one defining trait. They were bound to the sun. Gravity held them in its grip. Whether on circular orbits or elongated ellipses, their paths curved back upon themselves. Even the most eccentric comets, those that carried their frozen bodies far into the outer darkness, were still tethered. They would return, sooner or later, their courses predictable, their cycles endless. This is the essence of a solar system. A family of bodies linked by one star's gravity, each orbiting according to its place. They may collide, fragment, or change, but they remain members of the same gravitational household. An interstellar object is something different altogether. Its orbit is not closed, but open, hyperbolic. Its path is not a loop, but a line sweeping inward and outward, never to return. It is not bound to the sun. It belongs to no family here. It enters from beyond, spends a brief time in our skies, and departs again into the vastness. This is why astronomers speak of visitors. These bodies do not settle here. They do not repeat their appearances. They pass through, noticed only if our instruments are sharp enough to see them, and then they're gone. Their very nature is impermanence. The contrast could not be sharper. Take, for example, Halley's Comet. Every 76 years, it returns, its bright tail unfurling across our skies. Ancient civilizations saw it, and our descendants will see it again. It is bound to the sun, caught in its rhythm. Halley is not a visitor, it is a resident, albeit one that travels far before circling back home. Now place beside it an object like 3I ATLS. It does not return. Its orbit does not repeat. Once past, it is lost forever, receding into the interstellar void. If we see it at all, it is only once, in one human lifetime, during one fleeting window of observation. That transience is what makes it a visitor rather than a neighbor. But the word carries something more, a subtle shift in perspective. To call Atlas a visitor is to admit that the solar system itself is a kind of place, with boundaries, thresholds, and a sense of inside and outside. It is to recognize that our sun's domain is not the whole of reality, but one room in a larger cosmic mansion. The arrival of Atlas reminds us that there are doors and windows in that mansion, and that now and then someone passes through them. The term also emphasizes perception. For how many billions of years did objects like Atlas pass silently through the solar system, unseen and unnamed? They were no less visitors then, but they were ghosts, present yet unnoticed. Only with the advent of modern surveys like Atlas, Pan-STARRS, and others have we begun to notice these passerbys. The act of seeing transforms them. They are no longer anonymous fragments adrift. They are visitors, observed and acknowledged. This is not merely poetic. It is deeply scientific. The difference between bound and unbound bodies is fundamental to celestial mechanics. It is written in the mathematics of orbits, in the energy of trajectories. Bound bodies have negative orbital energy relative to the sun. They cannot escape. Unbound bodies, like Atlas, have positive energy. They are free. Their paths are hyperbolic, not ellipses. Their speed at infinity, the velocity they will carry forever, is greater than zero. That technical difference is profound. It means that Atlas is not just passing through, it is passing by with no possibility of capture. Its course through our solar system was a single curve, dictated by gravity's pull, but never chained to it. This is what separates the visitor from the resident. Astronomers sometimes describe interstellar objects as interlopers, but visitor carries more nuance. Interloper implies intrusion, as though the object does not belong, but visitor implies encounter. It suggests that the object brings something with it: information, perspective, mystery. In this sense, the label is as much cultural as scientific. It reflects our human tendency to see meaning in transience, to view the brief arrival of something from beyond as significant. The difference becomes clearer when we consider the other two known interstellar objects. Oumuamua, the first, was immediately labeled a visitor, even in its Hawaiian name, a messenger from afar arriving first. Its trajectory was hyperbolic, its motion unbound. Borisov, the second, was likewise a visitor. It looked like a comet, behaved like a comet, but its path was not cyclical. It would not return. By the time Atlas appeared, the terminology was established. Astronomers knew what they were seeing, and they knew what to call it. A visitor. Not ours, not bound, but passing through. This language also reflects the way such discoveries alter our view of the galaxy. For centuries, we imagined star systems as isolated. Planets and comets belong to their stars, circling endlessly within their own boundaries. But the arrival of interstellar visitors shows that the galaxy is porous. Material does not stay confined. It drifts, it wanders, it crosses from one star's domain to another. To call Atlas a visitor is to recognize this flow. It is to acknowledge that the solar system is not sealed, but open, connected by the movement of objects across interstellar space. And there is something humbling in that recognition, for if objects can visit us, then we too are not isolated. Fragments of our own solar system must have also been cast outward, set adrift among the stars. Somewhere, orbiting another sun, another civilization, if such civilizations exist, may one day notice a faint object in their sky. They may calculate its path, trace its hyperbolic curve, and realize that it came from far away. They may label it a visitor, just as we did with Atlas, and perhaps, unknowingly, they may be watching a fragment of our own home. The visitor label, then, is not just about Atlas. It's about perspective. It's about recognizing our place in a galaxy where movement and exchange are constant, even if invisible most of the time. It's about understanding that the borders of the solar system are not walls, but thresholds, crossed by wanderers from time to time. To call 3i ATLS a visitor is to admit that we live in a house with doors, and sometimes those doors open. The label also shapes how we think about meaning. For when something visits, we ask why. We ask what it brings. With Atlas, the questions multiply. What does its composition tell us about other star systems? What clues lie in its brightness, its fragility, its behavior near the sun? And beyond the science, there is the deeper, almost philosophical question. Are we meant to see these objects as messages, or simply as accidents of gravity? Science may prefer the latter, but the human imagination gravitates toward the former. Visitors, after all, suggest intention, even when none exists. We can't help but wonder whether the universe itself is sending reminders, fragments from afar, crossing our skies to remind us that we are not alone in the galaxy. This is why the visitor label persists. It captures both the scientific reality that Atlas is unbound, fleeting, and transient,
and the human response, that its arrival feels significant, like a meeting, however brief. And so 3I ATLS joins the short but growing list of interstellar visitors, each one a reminder that the solar system is part of a larger community, one that we are only just beginning to perceive.
Every celestial object carries a story, not only in its orbit, but in the light it reflects. For astronomers, photons are the primary language of observation. The faint glow of 3I Atlas, captured by telescopes during its brief passage, was more than just a point of light in the sky. It was a data stream, a coded message revealing clues about its shape, spin, and behavior. One of the first features scientists analyzed was its brightness variation. As Atlas traveled through the inner solar system, it did not shine with uniform intensity. Its reflected light fluctuated subtly, waxing and waning over hours and days. These variations are not random. They carry information about the object's rotation, its surface properties, and potentially even its structure. To the human eye, such changes would be imperceptible. But through the precise measurements of multiple observatories, astronomers could detect patterns. Brightness variation occurs when an object rotates, presenting different facets to the sun and consequently to our telescopes. Peaks in brightness correspond to surfaces that reflect more light, perhaps because they are smoother, lighter in color, or more reflective. Dips suggest rougher, darker, or less reflective regions. For Atlas, these variations hinted at a body that was irregular in shape. Unlike spherical asteroids or comets with near-uniform bodies, Atlas reflected light unevenly. Some regions glimmered briefly, while others seemed to vanish into shadow. This pattern suggests that Atlas was elongated or perhaps fractured, a shard rather than a monolithic rock. Its rotation, inferred from the brightness cycles, gave scientists an estimate of its spin period. Rotation is more than a simple spin. It tells a story of forces endured over time. A fast spin may indicate past collisions or ejection events, perhaps when the object was hurled from another star system. A slow, steady rotation might suggest a more gradual journey, shaped primarily by thermal forces and weak gravitational nudges across interstellar space. For Atlas, early estimates suggested a rotation period on the order of several hours. This is comparable to many comets and asteroids within our solar system, indicating a dynamic yet stable spin. Combined with its irregular brightness, it painted the picture of an object that had survived long and lonely travels, its rotation maintaining a steady, almost stoic rhythm despite the millennia of interstellar drifting. Beyond brightness and rotation, astronomers examined its physical behavior near the sun. Unlike Borisov, which exhibited a pronounced cometary tail, Atlas showed only subtle indications of activity. Its faint glow suggested it may have been partially volatile, releasing small amounts of gas or dust when warmed by solar radiation, but it was far less dramatic than typical comets entering the inner solar system. This subtlety raised questions. Was Atlas primarily rocky, icy, or a mix of both? Did it possess a fragile structure, prone to crumbling under heat and gravitational stress? Some researchers speculated that its faint activity indicated a dormant comet-like composition, an object with volatiles trapped deep inside, only weakly responding to solar warming during its brief passage. Others suggested it might be a fragment of a larger body, broken off and slowly disintegrating as it approached the sun. The data also provided insight into its albedo, the measure of how much light it reflects. Atlas was relatively dark, reflecting only a small fraction of sunlight.
This darkness is consistent with many outer solar system bodies and interstellar fragments, which accumulate layers of space-weathered material over eons. Such surfaces can be coated in complex organics, carbon-rich dust, or desiccated ices, all of which absorb light rather than reflecting it. Another important feature came from subtle changes in trajectory. High-precision measurements detected minute deviations from the predicted hyperbolic path. These could result from outgassing, tiny jets of gas exerting force on the body, or from uneven mass distribution affecting its motion. Even small changes provide critical clues to composition and structure. For Atlas, the observed deviations were minimal, suggesting that any outgassing was weak and sporadic, reinforcing the idea that it was not an active comet in the traditional sense. Rotation and brightness variations together tell the story of physical resilience. To survive interstellar travel, an object must withstand not only the vacuum of space, but also exposure to cosmic radiation, micrometeoroid impacts, and tidal stresses during close encounters with stars. The patterns observed in Atlas suggest it was durable, yet fragile, a survivor molded by both its ejection from another system and the millions of years drifting through the void. Comparisons with other interstellar objects deepen this narrative. Oumuamua, the first detected interstellar visitor, exhibited extreme brightness variations, implying a highly elongated shape, potentially 10 times longer than wide. Its rotation period was unusual, and it showed unexpected accelerations. Borisov, on the contrary, was a more conventional comet, with clear outgassing, a visible tail, and predictable brightness fluctuations. Atlas falls somewhere in between. Its brightness variations were measurable but moderate, its rotation steady but unremarkable, and its activity subdued. These signs in the data suggest that interstellar objects may not be a single class, but a spectrum. Some are elongated, tumbling shards. Some are icy comets. Some may even be porous rubble loosely held together by gravity. Atlas provides a critical data point on this continuum. Brightness also offers a window into surface heterogeneity. The fluctuations recorded imply that different areas of Atlas reflect light differently. Perhaps some sections are covered in silicate dust, while others retain frozen volatiles. Perhaps collisions in its home system left scars and fractures, producing facets that catch sunlight at different angles. Each flicker in brightness is a whisper from the surface, a subtle signal decoded by careful analysis. Rotation affects more than light. It affects stability. Rapid or irregular spinning can induce structural stress, leading to cracking or fragmentation. For Atlas, its rotation appeared moderate, consistent with a stable body, yet the very fact of its rotation, combined with minor changes in brightness and trajectory, suggests a complex internal structure. It may not be a solid monolith, but a patchwork, resilient yet susceptible to disruption. Physical behavior, brightness, rotation, all are signs in the data that together allow astronomers to reconstruct the life of this interstellar visitor. They tell us about its journey, its composition, its endurance, and its vulnerability. In a sense, they are fingerprints, each one unique, each one preserving the memory of where the object has been. Through these measurements, Atlas transforms from merely a point of light into a narrative entity. Its changing brightness is a heartbeat. Its rotation is a silent rhythm of motion. Its faint activity is a whisper of distant origins. And its trajectory is a line connecting unknown worlds across the galaxy, a path linking us to the stars from which it came. Even the absence of dramatic features is meaningful. Unlike a comet blazing with dust and ice, Atlas's faint signs suggest a quiet resilience, a muted testimony to the long, lonely journey it has endured. Its faintness challenges observers, yet it also marks the object as typical,
Perhaps most interstellar visitors are subtle, unremarkable, and only detectable with patient observation and sophisticated instruments. By examining brightness variation, rotation, and physical behavior, astronomers are beginning to read the story of Atlas, even though it is a story written in light years and eons. Each flicker of light encodes a moment of its history. Each spin cycle preserves its response to forces far beyond human scales. Even the faintest glimmer is a record of billions of years of interstellar motion. Atlas reminds us that data is not just numbers, it is narrative. Every measurement, every fluctuation, every minor deviation from expected behavior is part of the story of this visitor. In its light, we see evidence of origin, journey, endurance, and encounter. In its motion and brightness, we trace the faint outlines of a world we will never visit, yet whose presence has briefly touched our own. And in this there is wonder. For a tiny, faint object passing silently through the solar system carries within it the history of another star system, the motion of the galaxy, and the resilience of matter cast adrift across interstellar space. Its brightness variations are not merely
Shape is destiny in the cosmos. The form of an object dictates how it moves, how it reacts to the sun's light, how it interacts with gas and dust, and ultimately how it survives the harshness of space. For interstellar objects like 3I Atlas, shape is also a record, a clue to its history, its formation, and the forces that cast it into the void. Astronomers have pieced together a preliminary picture of Atlas from the data collected during its brief visit. Brightness variations, rotation rate, and subtle activity hint at its physical character, but the conclusions remain tentative. Without spacecraft visits, without direct imaging at close range, we rely on inference, models, and comparison to similar objects. And even then, every model carries uncertainty. One possibility is that Atlas is comet-like, an icy body with volatile materials that sublimate as it nears the sun. Such a form is familiar to astronomers. Within our solar system, comets are often irregular, lumpy, and asymmetric. They may harbor deep ice pockets covered by dust and rock. When heated, gas escapes, creating a visible coma and sometimes a tail. Atlas showed only faint signs of activity, far less than a typical comet. Yet even weak outgassing can shape the body over time. Ice sublimation can create fissures, weaken structural cohesion, and even alter spin rates. In this scenario, Atlas would resemble a small, icy cometary fragment, perhaps a few hundred meters across, with a lumpy, uneven surface. Its rotation, inferred from light fluctuations, could be explained by asymmetric mass distribution or localized sublimation. But there is another possibility. Atlas could be elongated, a long, narrow shard rather than a compact lump. This possibility recalls the first interstellar visitor, Oumuamua, whose extreme brightness variations suggested a length-to-width ratio of up to 10:1. If Atlas shares this feature, it would not be spherical or typical, but a stretched object, tumbling end over end as it passed through the inner solar system. An elongated shape has consequences. It can influence how sunlight reflects off the surface, producing pronounced brightness variations. It affects rotation, potentially inducing chaotic tumbling rather than steady spin. And it changes the way forces act on it. Even weak solar radiation pressure can subtly alter the trajectory of a highly elongated object. Comparisons to Oumuamua deepen the mystery. That first interstellar object defied easy classification. Was it an icy body coated with rock, or a fragment of a planet-like object? Was it a shard, elongated by collision, or shaped by tidal forces near a massive star? Astronomers remain divided. Its brightness variations and unusual accelerations sparked debate for years, raising questions about whether some interstellar objects might even be artificial in origin, or at least highly atypical in structure. Atlas does not appear to be as extreme as Oumuamua, but it may share certain traits. Its brightness variations are moderate, suggesting a less dramatic elongation, yet still hinting at asymmetry. Its rotation appears steady, not chaotic, implying a relatively balanced shape. Its activity is weak, possibly indicating a surface dominated by dust or rock with minor volatiles beneath. In this sense, Atlas may represent a more conventional, yet still fascinating member of the interstellar object class, a midpoint between typical solar system comets and the enigmatic extremes of Oumuamua. Models of its shape also depend on surface properties. Darker areas absorb sunlight and heat more efficiently, while reflective regions may remain cooler. Variations in albedo across its surface can mimic the effect of shape in observed brightness fluctuations. Thus, what appears to be a highly elongated form could in part be a patchwork of light and dark areas. Disentangling shape from surface heterogeneity is one of the key challenges astronomers face when reconstructing Atlas's structure. Another factor is fragility. Interstellar objects endure harsh conditions over immense timescales. Cosmic rays bombard their surfaces, micrometeorites erode them, and the thermal extremes of deep space act slowly but persistently. Atlas's apparent modest activity near the Sun may reflect a body that has survived billions of years, yet is brittle and possibly fractured. A comet-like fragment could break apart if it rotates too quickly, while an elongated shard may resist disintegration due to its rigid form. Simulations have been used to explore these possibilities. Computational models can test how light curves change under different rotation states, shapes, and surface compositions. By comparing predicted brightness fluctuations with observed data, astronomers narrow down the most likely configurations. For Atlas, these simulations suggest a body that is neither perfectly spherical nor extremely elongated. Perhaps a moderately irregular shape, spinning in a steady pattern, with subtle surface heterogeneity producing its observed light curves. Its physical structure also provides hints about its history before reaching our solar system. An elongated or fractured body may have been ejected during a violent event, perhaps a collision in its home system or a tidal encounter with a massive planet or star. A more compact, comet-like form may suggest gradual ejection from the outer regions of a planetary system, where it was loosely bound and nudged into interstellar space over time. Either scenario speaks to the complexity of planetary system dynamics beyond our own Sun. Atlas's shape is also tied to its survival in the inner solar system. A fragile body might disintegrate entirely under solar heating or tidal forces, leaving only dust and fragments. Yet Atlas persisted long enough for detailed observation, implying sufficient structural integrity. Its modest activity indicates that while it was influenced by solar heating, it was not catastrophically altered, at least during the brief window we observed it. Comparisons with solar system comets offer additional insight. Most comets are irregular, lumpy, and active, displaying tails when they near the Sun. Atlas differs in two key ways: its faint activity and its potential asymmetry. It does not display a dramatic coma, yet its light curve reveals subtle irregularities. These features hint at a body shaped by forces beyond our solar system, molded over millennia in environments unfamiliar to our Sun. In some ways, Atlas bridges the gap between the ordinary and the extraordinary. Its form may be more conventional than Oumuamua, yet it is still unlike any typical solar system body. Its brightness variations, rotation, and weak activity reveal a complex object, one that is neither monolithic nor entirely fragmented, neither comet-like nor impossibly elongated. It exists in an intermediate category, a visitor with a story encoded in shape and light. Its structure also raises questions for future observation. If similar interstellar objects are detected, will they conform to Atlas's moderate irregularity, or will they display extremes like Oumuamua? Could a spectrum of shapes exist, reflecting the diversity of planetary system formation across the galaxy? Atlas provides a critical data point, a benchmark for understanding the range of possible structures. Ultimately, the shape and structure of Atlas are central to understanding it as a visitor. They determine how it reflects sunlight, how it rotates, how it interacts with the solar environment, and how it survives. They carry signatures of its origin, the processes that ejected it from another star, and the long journey it has endured through interstellar space. In this sense, Atlas's form is more than geometry. It is a record of cosmic history, a relic of distant worlds, and a testament to the diverse possibilities of objects wandering the galaxy. By studying its shape and structure, astronomers decode a story written across light years, a story of ejection, drift, and passage through the unknown. And as we compare Atlas to Oumuamua and Borisov, we begin to glimpse the variety that interstellar objects can exhibit. Some may be elongated, shards, tumbling unpredictably. Some may be comet-like fragments, fragile yet enduring. Atlas, with its moderate irregularity and subtle activity, occupies a middle ground, hinting at the broad spectrum of visitors waiting to be discovered. Its shape, its rotation, its faint glow, all these signs in the data reveal a body that is both ordinary and extraordinary. Ordinary in that it shares traits with cometary fragments we understand. Extraordinary in that it has traveled across the galaxy to visit us, carrying with it the silent story of a distant system we may never see. And so the question of shape is not merely technical. It is a question of identity. By understanding the form of Atlas, we come closer to understanding its origin, its history.
When we look at the night sky, what we see is light, starlight, sunlight, reflected off surfaces millions or billions of kilometers away. But to astronomers, light is more than illumination. It is information. The spectrum of that light, how it is absorbed, emitted, or scattered, carries secrets about composition, structure, and history. In the case of 3I/Atlas, the faint photons captured by telescopes hold the key to its most intimate mysteries, what it is made of, and what that material tells us about its origin. Spectroscopy is the method of choice. By splitting light into its component wavelengths, scientists can detect characteristic absorption lines, which act like fingerprints for chemical elements and compounds. Hydrogen, carbon, nitrogen, silicates, and ices all leave distinct signatures. In theory, a spectrum can reveal whether an object is icy, rocky, or a mixture of both. But interstellar visitors like Atlas present a unique challenge. They are faint, fleeting, and far away. Observations must be made quickly, and even then, the data is often noisy, subtle, and difficult to interpret. Preliminary spectra of Atlas suggested that it was relatively dark, with low albedo, reflecting only a small fraction of incoming sunlight. This places it in the company of many outer solar system bodies and typical comets, which often have carbon-rich surfaces coated in dust or complex organics. Such a dark coating could indicate exposure to cosmic rays over eons, which chemically alter surface materials, turning ices and organics into a hardened, desiccated crust. Yet darkness alone tells only part of the story. Spectroscopic observations seek to determine whether volatile ices, water, carbon monoxide, carbon dioxide, or ammonia exist within or on the surface. For Atlas, evidence of outgassing was faint,
far subtler than that of 2I/Borisov, the interstellar comet detected just 2 years earlier. Borisov had revealed robust signatures of carbon monoxide and cyanide compounds, betraying a rich chemical composition similar to solar system comets. Atlas, in contrast, seemed almost inert. This raises an intriguing possibility. Perhaps Atlas is depleted in volatiles, or its surface is insulated by a thick layer of dust and rock that prevents sublimation. If so, it may represent a class of interstellar objects distinct from typical icy comets, fragments that survive long interstellar journeys in a dormant state, resistant to sublimation when exposed to stellar heat. Alternatively, weak activity could indicate small amounts of ice buried deep within, only minimally affected during its brief encounter with the sun. Spectra can also hint at mineralogical composition. For instance, silicate-rich surfaces produce characteristic absorption features at certain infrared wavelengths. Observations of Atlas suggest that its surface may contain a mix of silicates and organics. This is consistent with materials formed in protoplanetary disks, where dust, ice, and organic compounds coalesce to create the building blocks of planets and smaller bodies. In other words, Atlas carries the chemical signature of another star system, a distant origin encoded in its material makeup. But there is more to the mystery. Some spectral data suggest subtle differences from both Borisov and typical solar system comets. While Borisov's spectrum clearly identified familiar cometary compounds, Atlas's data is less definitive, leaving room for speculation. Could it contain unusual organics, materials not commonly found in our solar system? Could its surface be partially processed, shaped by radiation in interstellar space, producing a composition unlike any object we have studied up close? The possibility of something stranger cannot be ruled out. Oumuamua, the first interstellar object, presented similar enigmas. Its unusual acceleration and lack of observable outgassing led some scientists to speculate that its surface could be covered with hydrogen ice, or even that it might be a fragment of exotic material, perhaps shaped by processes unknown to our solar system. Atlas does not display the same extreme anomalies, yet its subdued activity and spectral ambiguity suggests that interstellar objects may be chemically diverse and that we have only scratched the surface of what these visitors can reveal. Ice content, dust coating, organic compounds, silicates, all of these factors contribute to an understanding of Atlas's physical behavior. The weak outgassing, subtle activity align with its inferred shape and rotation. An elongated or irregular object with a dust-covered surface would naturally display minimal sublimation. Its brightness fluctuations and rotational stability further support the idea that any volatile ices are buried or sparse. Comparisons with solar system analogs help contextualize these findings. Jupiter family comets, for example, often show strong activity as they approach the Sun, producing prominent comae and tails. Long-period comets from the Oort cloud, though similar in composition, can exhibit more variable behavior depending on their histories. Atlas behaves differently from both, suggesting that interstellar objects are not mere analogs of local comets, but a distinct class. Their composition reflects the environments of other star systems and the long-term effects of interstellar travel. Even the lack of detectable gas is informative. It implies that Atlas's surface is hardened, or that any ice is too deeply buried to react quickly to the sun's heat. Such a structure could arise from millions of years drifting through space, where cosmic rays, micrometeoroids, and thermal extremes slowly erode surface volatiles, leaving behind a carbon-rich crust. Over time, these processes may produce an object that is stable, dark, and weakly reactive, capable of surviving a hyperbolic journey across the galaxy. Another layer of intrigue comes from minor deviations in trajectory. Precise measurements hinted at small, almost imperceptible accelerations, which could be explained by very weak outgassing. If Atlas contains hidden ices, the sublimation may be enough to nudge it slightly without producing a visible tail. This subtle behavior aligns with the spectral evidence. A body composed primarily of dust and rock, with ice confined beneath a protective surface. Spectral studies also allow for speculation about organic content, which carries profound implications. Carbon-rich materials are common in comets and asteroids, but the particular mix of organics in interstellar objects may differ. Complex molecules could reveal formation conditions in distant protoplanetary disks, offering a glimpse into the chemistry of another star system. Atlas, faint as it is, may hold such clues. Its composition may encode the history of organic chemistry in environments far from the Sun. All of this underscores the essential mystery of interstellar composition. Atlas's spectral data does not provide simple answers. Instead, it raises questions. Is it a rocky, dust-covered fragment of a disrupted planetesimal? A dormant, icy body, resistant to sublimation? Or does it contain unexpected compounds, formed under conditions unfamiliar to our solar system? Each possibility expands our understanding of the diversity of material in the galaxy. The comparison with previous interstellar objects is instructive. Oumuamua appeared rocky and possibly metallic, with unexplained acceleration and lack of visible outgassing. Borisov, by contrast, was a rich, icy comet, full of volatiles and dust. Atlas falls somewhere in between. It is darker than Borisov, less active, and spectrally ambiguous, yet it shows subtle hints of familiar compounds. In this way, Atlas reinforces a growing realization. Interstellar objects may not conform to a single category, but span a continuum, each carrying unique chemical signatures from their parent systems. In essence, the composition mysteries of Atlas remind us that the galaxy is chemically diverse, and that our solar system may be both ordinary and exceptional. Each visitor that passes through brings with it not just mass and momentum, but molecular memory, a record of conditions in faraway planetary systems. Every spectrum we capture is a story. Every faint signal is a clue. Through careful analysis of spectra, astronomers continue to piece together Atlas's makeup. Dust, ice, organics, silicates, all are possibilities, and all carry meaning. Its faint activity, subtle brightness variations, and spectral ambiguity make it a puzzle, a challenge, and a gateway to understanding the broader population of interstellar bodies. And so, Atlas's composition remains a tantalizing mystery. It is a visitor not only in space, but in knowledge, arriving briefly in our observation.
Even after careful observation, even after days, weeks, and months of analysis, 3I Atlas refuses to yield all of its secrets. Its trajectory, behavior, and physical properties are known only in part, leaving a host of unanswered questions that continue to puzzle astronomers. Each observation provides clues, yet each clue also reveals new mysteries. In the cosmos, the more we learn, the more we realize how little we truly know. One of the first puzzles lies in Atlas's trajectory. Its path through the solar system was hyperbolic, confirming that it was unbound and interstellar in origin. Yet even in this simple classification, subtle oddities appear. High-precision measurements of its motion revealed small deviations from a purely gravitational trajectory, deviations that cannot be entirely explained by the sun's influence alone. These anomalies are reminiscent in some ways of the mystery surrounding Oumuamua. That first interstellar object showed unexpected accelerations, leading to speculation about non-gravitational forces, outgassing, radiation pressure, or even more exotic explanations. Atlas is less extreme, but hints of deviation exist, prompting questions about the forces acting upon it. One possibility is outgassing. Comets within our solar system often deviate from gravitational predictions due to jets of gas escaping from their surfaces. These jets act like thrusters, subtly pushing the body off its expected path. Atlas showed only faint signs of activity, yet even minor sublimation of volatile ices could produce measurable effects on its trajectory. The challenge is quantifying how much gas is required to explain the observed deviations, and whether the sparse evidence of activity matches the calculated forces. If outgassing is indeed responsible, it implies a delicate balance. Atlas would need just enough ice to produce tiny thrusts, yet not so much as to create a visible coma or tail. Its dark, desiccated surface may conceal pockets of volatile material buried beneath a protective crust. As sunlight penetrates the surface, these hidden ices could sublimate irregularly, producing subtle, uneven forces that nudge the object along its path. But outgassing may not be the full story. Observations suggest that Atlas's motion could include contributions from other factors: rotational effects, structural asymmetry, or even radiation pressure from sunlight. Each of these forces is small, but in the context of a lightweight, elongated, or irregularly shaped body traveling at tens of kilometers per second, even tiny effects can accumulate, producing deviations detectable by the most precise instruments. The trajectory anomalies prompt a broader question. How typical are such deviations for interstellar objects? With only 3 known examples, Oumuamua, Borisov, and Atlas, it is difficult to establish norms. Do all interstellar visitors experience subtle accelerations due to outgassing or radiation pressure? Or are these anomalies unique to each body, reflecting individual histories and compositions? Atlas adds a crucial data point, but the sample size remains painfully small. Beyond trajectory, other unanswered questions arise from its physical behavior. Its rotation appears steady, yet the irregular shape suggested by brightness variations implies that torques could act upon it. Could the combination of spin and solar heating induce internal stress? Could Atlas fracture in the future, leaving a trail of fragments invisible to our telescopes? These are questions that cannot be answered without direct observation. Yet they underscore the fragile, dynamic nature of interstellar bodies. Another intriguing question concerns origin. While its incoming direction hints at a region near Ursa Major, precise identification of a parent star is impossible with current data. The galaxy itself moves, and stars drift over millions of years, erasing clear tracks. Atlas could have been wandering for millions or even billions of years. Its material, shape, and motion encode clues about its birthplace, but decoding them is an enormous challenge. What kind of planetary system produced it? Was it ejected by a massive planet, a binary star, or a violent collision? Each scenario leaves different signatures in structure, composition, and trajectory, but interpreting these signatures requires assumptions we cannot fully verify. Even composition raises questions. Spectroscopy hints at a mix of dust, rock, and possible ices, but the details remain ambiguous. Is the surface uniform, or does it contain pockets of more volatile material? How does its chemical makeup compare to solar system comets, or to other interstellar objects? Atlas's subtle signals may conceal surprises, unexpected organics, unusual mineralogy, or structural anomalies that challenge our models of planetary formation beyond the Sun. These unanswered questions extend to behavior under solar heating. Atlas's faint activity contrasts sharply with Borisov, which erupted with visible jets and dust emission. Did Atlas once resemble a more active comet, gradually depleted by interstellar radiation over millions of years? Or is it inherently a low-activity object, formed in conditions that produced a more inert body? Understanding its response to the Sun is critical for interpreting its internal structure and its potential survivability. Even its apparent stability poses questions. An elongated or irregular body like Atlas should experience torques from solar radiation, potentially altering rotation or producing chaotic tumbling. Yet observations suggest relative stability. Does this indicate internal cohesion, a balanced mass distribution, or mere coincidence during the brief window of observation? Could future interstellar objects reveal more dramatic behavior, exposing limits to what Atlas can teach us? The anomalies in trajectory and behavior also invite speculation about more exotic explanations. While conventional physics provides plausible mechanisms, outgassing, radiation pressure, or rotation, some have wondered whether other forces could be at play. Oumuamua prompted controversial hypotheses, including the possibility of artificial origin or unusual material properties. Atlas is less extreme, but its subtle deviations continue to fuel debate. Scientists remain cautious, emphasizing that extraordinary claims require extraordinary evidence, but the mystery persists, and it compels us to remain vigilant and curious. These questions are not purely academic. Understanding interstellar objects has profound implications for planetary science. Each anomaly, each deviation from expectation informs models of planetary system evolution. How are bodies ejected into interstellar space? What fractions survive long journeys? How do they interact with stars they pass? Atlas, even in its brief visit, provides data that helps answer these questions, or at least frame them. Moreover, these unanswered questions illustrate the limits of observation. For most of human history, interstellar objects were invisible. They passed silently through the solar system, unnoticed, leaving no record. Only with modern surveys, precise instrumentation, and global collaboration can we detect them, measure their motion, and begin to interpret their properties. Yet even now, with Atlas in the telescope's view, our understanding remains partial. We see outlines, hints, and patterns, but the full story remains hidden, waiting for future observation or perhaps a closer encounter that may never come. In the end, Atlas reminds us that science is often a dialogue with the unknown. Trajectory oddities, weak activity, spectral ambiguity, and subtle rotation are not failures of understanding. They are invitations. They challenge astronomers to refine models, test assumptions, and expand the boundaries of knowledge. They remind us that the galaxy is vast, its contents diverse, and its processes often stranger than expected. And yet the very act of questioning reveals progress. Each unanswered question highlights what we do know. Atlas is interstellar, unbound, traveling at extraordinary speed, shaped irregularly, faintly active, and chemically complex. Its trajectory anomalies are small, yet measurable. Its subtle signals are enough to intrigue, enough to inspire, enough to ensure that it will be studied long after it has vanished from sight. Atlas's visit is fleeting, but its mysteries endure. Its anomalies, both in motion and in behavior, underscore how little humanity has observed of the interstellar population. For every Atlas, there may be thousands, silently drifting, invisible to even our most sensitive surveys. And each of these objects carries questions about origin, composition, structure, and the forces that govern their motion. In this sense, the unanswered questions are themselves a message. They invite us to look deeper, to develop better telescopes, more sensitive detectors, and more refined models. They remind us that the universe is not merely a catalog of bodies obeying Newtonian mechanics. It is a living laboratory, constantly surprising us with objects that defy expectations, challenge assumptions, and inspire wonder. The trajectory oddities, the energy discrepancies,
The trajectory of 3I-ATLAS, like all celestial objects, is defined by the impartial laws of physics. It follows a hyperbolic path determined by its velocity, its angle of approach, and the gravitational influence of the Sun and planets. To astronomers, this movement is mathematics, predictable and inevitable.
And yet, for millennia, humans have looked at the sky and seen more than physics. They have seen meaning. They have seen signs. They have asked not only how an object moves, but why. So when ATLAS appeared, sweeping in from the darkness of interstellar space, brushing past our sun and then vanishing once more into the void, it was natural to wonder, is this motion purely coincidence, or is it, in some deeper sense, a message? The idea of celestial symbolism is ancient. In every culture, the heavens were regarded as more than empty space. A comet blazing across the sky might be seen as an omen of war or change. A wandering star could be interpreted as divine intervention. Even eclipses, now explained with precision, once carried spiritual weight. The movement of the heavens has always stirred questions of fate, destiny, and meaning. ATLAS, with its singular trajectory, echoes this tradition. It is not like the repeating planets or the cyclical comets we know. It will not return in a predictable orbit. Its path is unique, a one-time crossing, a visitor whose presence can never be replicated. To the human imagination, this uniqueness begs interpretation. Was it simply chance that we saw it at all? Was its arrival in this moment of history nothing more than random timing? Or could its motion, its entry, its brief shining, its exit be read as a form of communication? On a purely scientific level, the answer is clear. ATLAS moves according to Newtonian mechanics, shaped by gravity, momentum, and perhaps faint whispers of outgassing. There is no intention behind its path, no guiding hand, no encoded message in its curve through the solar system. It is the outcome of natural forces, as indifferent as the falling of rain. But science and philosophy are not mutually exclusive. While physics explains how, philosophy asks what it means to us. A traveler passing once through our skies, never to be seen again, feels like a story, like a metaphor. It feels like a line drawn across the heavens, pointing to questions about our place in the galaxy. Some have wondered if interstellar objects like ATLAS might be more than just natural fragments. Could they, in theory, be artifacts, sent deliberately or accidentally from distant civilizations? Oumuamua sparked that debate when its trajectory showed unexplained acceleration, leading some researchers to consider whether it might be artificial, perhaps a probe or a fragment of alien technology. ATLAS does not display the same extreme oddities, but the very existence of such visitors continues to stir speculation. Even without invoking extraterrestrial design, one can ask, is its movement symbolic? Symbolism does not require intent. A rainbow after a storm is not deliberately placed, yet humans interpret it as beauty, as hope. A falling star is not aimed at us, yet we make wishes upon it. In the same way, ATLAS's hyperbolic curve may hold meaning simply because we witnessed it. Its fleeting passage becomes a reminder of impermanence, of encounters that happen once and are gone forever. Coincidence, too, has power. The fact that humanity is only now, in this century, capable of detecting interstellar visitors carries symbolic weight. For billions of years, countless such travelers must have crossed our skies unnoticed. Only with modern telescopes and global observation networks have we been able to catch them. That we saw ATLAS at all, this faint speck from another star, feels like a convergence of timing and technology. Perhaps coincidence is the universe's way of reminding us that discovery comes when we are ready to perceive it. Consider also the elegance of its path. It comes from the stars, its wings close to the sun, and then it is gone, never to return. This motion mirrors the arc of a messenger: arrive, deliver, depart. The message may not be intentional, but it resonates. It tells us that we are not isolated. It reminds us that our solar system is not an island, but part of a vast, dynamic galaxy in which material constantly drifts, crosses, and connects. And what message do we, as humans, project onto it? Perhaps ATLAS tells us that the universe is alive with motion, that even the emptiness of interstellar space is not barren, but filled with fragments of distant worlds. Perhaps its motion says that our story is not confined to this sun and these planets, but tied to the galaxy at large. Or perhaps it speaks of impermanence, the truth that encounters are fleeting, that chances to observe and learn must be seized before they vanish forever. There is a tension here between coincidence and design. From a scientific perspective, ATLAS's arrival is coincidental. Its ejection from a distant star system, its path across interstellar space, and its chance approach to the sun are all products of random celestial mechanics. Yet humans are pattern-seeking creatures. We search for meaning in randomness, for design in coincidence. That tension is what gives ATLAS its philosophical weight. If its path is coincidence, then the lesson may be humility. We are small, temporary observers of vast processes that unfold without us. If, against all odds, its path were design, if interstellar objects were somehow meant to cross our skies, then the lesson would be connection, that we are part of a wider dialogue in the galaxy, even if we cannot yet decipher the language. In both cases, ATLAS's movement stirs the same questions. Why now? Why here? Why us? These questions are not answered by physics alone, yet they shape our experience of discovery. They remind us that science does not exist in isolation from wonder. Data and numbers are critical, but so too are the meanings we assign to them, the stories we weave from the motion of stars and stones. One might imagine future generations looking back on these first interstellar discoveries as symbolic milestones. Oumuamua, Borisov, ATLAS, each a messenger of sorts, announcing that the galaxy is not silent, that it sends fragments across the void. Their paths may be random, but our encounter with them is real. To interpret that as a message is not unscientific, it is human. It is the blending of fact with meaning, observation with philosophy. ATLAS's hyperbolic curve is not only a scientific trajectory, it is also a metaphor for human existence. We too are travelers through time, passing once through the stage of history before vanishing into memory. Like ATLAS, we are fleeting, yet our passage leaves traces, questions, and echoes. To see our own impermanence reflected in the movement of a distant traveler is to recognize ourselves in the cosmos. So is ATLAS just a visitor, or is it something more? If we speak strictly in physical terms, it is a natural fragment, moving by chance, unmarked by intention. But if we allow ourselves to listen differently, to see symbolism in its path, to consider the resonance of its timing, then ATLAS is more than stone and dust. It is a mirror. Its motion reflects our own longing for meaning in the universe. Its fleeting presence is a reminder that every encounter, however brief, can hold significance. Its hyperbolic journey, once observed, becomes a message not from another civilization, but from the cosmos itself. And perhaps that is the deepest truth. A message does not require a sender. A message exists when it is received. By noticing ATLAS, by asking questions about its path, by wondering about coincidence and design, humanity has already transformed its trajectory into meaning. The faint speck of light crossing the solar system in silence has become a story in our minds, a sign in our sky, a movement we interpret as both science and symbol.
When a faint speck like 3I Upper ATLS is discovered, the first task of astronomers is simple in theory, yet immensely complex in practice. Measure, analyze, and classify. Science begins with data, and the data on ATLS, its brightness curve, its spectral lines, its orbital elements, provide a foundation for sober conclusions. The mainstream scientific view is clear. ATLS is a natural interstellar object, a piece of debris ejected from some distant planetary system, wandering the void for eons before chance carried it into our skies. Its hyperbolic trajectory proves it does not belong here. Its faint signs of cometary activity suggest volatile material beneath its surface. Its rotation and brightness variations, though irregular, are consistent with a body of modest size and complex shape. To astronomers, these features paint a familiar picture. Not familiar in the sense of local comets, but familiar in the sense of natural physics. A fragment of ice and rock, jostled by the forces of its home system, expelled into interstellar space, and now continuing on a path set long ago. In this view, ATLS is not extraordinary, it is expected. Billions of planetary systems are thought to eject such objects. Statistically, some will wander close enough for us to detect. We happen to see this one. But even within this framework, there are uncertainties. The trajectory shows slight deviations from a purely gravitational path, hinting at outgassing too faint to detect directly. The brightness variations suggest a shape that is irregular, perhaps elongated, but the details remain elusive. The composition inferred from spectra is murky, pointing to dust and possibly ice, but without the precision needed for definitive identification. Scientists acknowledge these gaps, but they do not leap to extraordinary conclusions. Instead, they assume that the anomalies fit within the wide range of natural variability. The cosmos, after all, produces endless diversity. Yet outside the cautious walls of mainstream astronomy, speculation blooms. The moment Oumuamua was detected, with its peculiar acceleration and its cigar or pancake-like shape, theories of artificial origin began to circulate. Could it have been a probe, a fragment of alien technology? The most controversial hypothesis proposed by Avi Loeb of Harvard suggested it might even be a light sail, an artificial construct pushed by starlight. That claim divided the scientific community, drawing both fascination and criticism. So when ATLS appeared as the third interstellar object, it entered a stage already prepared for speculation. Some asked, is this another messenger, another artifact disguised as a comet? Could these visitors be intentional, sent to pass near stars and perhaps collect data? The idea of design, though far outside mainstream consensus, inevitably colored the discussion. Alternative theories emerged, fueled by the same data that astronomers interpreted conservatively. The slight trajectory anomalies, instead of being attributed to faint outgassing, were framed as possible evidence of engineered propulsion or radiation manipulation. The irregular brightness changes, instead of being seen as natural tumbling, were imagined as structural panels or surfaces reflecting sunlight in unusual ways. The uncertain composition became a canvas for speculation. Metallic alloys, advanced composites, or exotic ices unknown to our solar system. Mainstream scientists resisted these leaps, pointing out that extraordinary explanations require extraordinary evidence. ATLS, they argued, provided no such evidence. The data fit well enough within natural cometary models, even if those models allowed for ambiguity. To invoke alien technology, they said, was to overextend imagination in the absence of necessity. Still, the line between science and speculation is not always as sharp as we might believe. Speculation, after all, often drives new questions. Oumuamua's anomaly sparked research into radiation pressure, into the fragility of interstellar bodies, into the limits of cometary models. Likewise, ATLS's ambiguities inspire new debates about how interstellar travelers evolve, how surfaces erode under cosmic rays, how small bodies behave after billions of years adrift. Even when speculation strays too far, it pushes science to refine its answers. The philosophical divide lies in method. Mainstream astronomy builds from data upward, refusing to claim more than the evidence supports. Alternative theorists often build from possibility downward, imagining what could be true if the universe were stranger than expected. One side anchors itself in caution, the other in curiosity. Both in their way are part of the human encounter with the unknown. Yet the contrast also reveals deeper cultural currents. For some, the idea that interstellar visitors might be artifacts is more than speculation. It is hope. Hope that we are not alone. Hope that the silence of the galaxy might someday break. Hope that the faint speck of light in a telescope might be a connection across unimaginable distances. For others, the hope is different, that natural explanations prevail,
that the universe remains a place of laws and patterns, not of mysteries beyond comprehension. ATLS, like Oumuamua before it, became a mirror for these hopes. When astronomers concluded it was most likely a fragment of natural rock and ice, they were reaffirming the stability of science, the reliability of physics. When speculators asked whether it could be more, they were expressing the hunger for wonder, for contact, for significance beyond the ordinary. In truth, both perspectives coexist. To deny speculation entirely would be to deny the curiosity that drives discovery. To indulge speculation without restraint would be to lose the rigor that separates science from story. ATLS stands at this intersection, a body defined by data, yet cloaked in imagination. And here lies the irony. Even as astronomers dismissed the wilder theories, they acknowledged how little we know about interstellar objects. With only 3 confirmed examples, no catalog exists from which to define norms. How big are they? How frequent? How diverse in shape, structure, and composition? Every new discovery reshapes the answers. In that sense, speculation is not only inevitable, but necessary, guiding the questions until more data arrive. So where does this leave 3I upper ATLS? For mainstream astronomy, it remains a natural fragment, likely cometary, faintly active, shaped by billions of years of interstellar exposure. Its anomalies are real, but explainable. Its mysteries are acknowledged, but not exaggerated. For alternative thinkers, however, it is an opening, a hint that the universe might hold secrets yet untold. Its trajectory and behavior can be read as more than random, more than natural, more than ordinary. The tension between these views will not resolve soon. Each new interstellar discovery will reignite the debate: natural or artificial, coincidence or design. Each new trajectory will be examined for signs, each anomaly magnified into meaning. Science will move steadily forward, but speculation will always trail alongside, whispering possibilities that data alone cannot silence. And perhaps that is the real value of ATLS in this conversation. It demonstrates that science and speculation are not enemies, but companions on the path of discovery. Science provides the anchor, speculation the sail. Without the anchor, we drift too far. Without the sail, we never leave shore. Together, they allow humanity to look at a faint speck from another star and see both physics and possibility, both measurement and meaning. 3I upper ATLS, in its brief appearance, reinforced the discipline of science while igniting the imagination of speculation. To astronomers, it is data. To dreamers, it is symbol. To the world, it is both. A natural fragment and a source of wonder. A traveler whose movement is studied with equations, yet interpreted with stories.
When 3I/Atlas appeared in our skies, faint and fleeting, most astronomers quickly filed it under the category of natural interstellar object. And yet, a different question lurks at the edges of that conclusion. What if it isn't entirely natural? What if Atlas, like its predecessor Oumuamua, opens the door to a far more provocative possibility, that some interstellar visitors could be artificial? The idea did not emerge from Atlas itself. It began with Oumuamua. Discovered in 2017, that first interstellar visitor defied easy explanation. Its brightness curve suggested a shape more elongated than any asteroid or comet ever observed. Its motion revealed subtle accelerations that could not be fully explained by gravitational forces. And most puzzling of all, there was little or no evidence of outgassing, the usual culprit when comets shift unpredictably in flight. For many scientists, these anomalies were intriguing, but still compatible with natural explanations. Exotic ices sublimating invisibly, a flattened pancake-like shape shedding mass in ways we could not easily detect. But for others, these explanations stretched the limits of plausibility. That tension opened the door to an extraordinary hypothesis. What if Oumuamua was not natural debris at all? What if it was an artifact, perhaps a fragment of alien technology, or even a probe, passing silently through our solar system? The most prominent voice behind this claim was Avi Loeb, an astrophysicist from Harvard.
He argued that Oumuamua's odd acceleration could be explained if it were extremely thin, like a sheet, capable of being pushed by radiation pressure from starlight. In other words, it might be a light sail, an artificial construct designed to travel between stars. The idea captured public imagination, igniting headlines and sparking debates that stretched far beyond academic journals. Most of the scientific community remained skeptical. The artificial hypothesis lacked hard evidence. It relied not on data pointing directly to alien design, but on the absence of a comfortable natural explanation. Yet the controversy surrounding Oumuamua left a mark. It reminded scientists and the public alike that when something truly strange crosses our skies, the possibility of artificiality cannot be dismissed outright. And so, when Atlas was discovered in 2019, it inevitably entered that same conversation. Was this new interstellar traveler another enigmatic anomaly? Could it too be a fragment, a probe, a sign of intelligence hidden within the flow of natural debris? The evidence, at least at first glance, seemed less sensational. Atlas behaved more like a comet. It showed faint signs of outgassing, producing a subtle coma and even hints of a tail. Its brightness curve, while irregular, did not demand the extreme interpretations that Oumuamua forced upon astronomers. In many ways, Atlas looked like the safer case, the object that reaffirmed natural explanations. And yet, questions remained. The trajectory still carried subtle deviations, small accelerations not fully accounted for by gravity alone. The shape was uncertain, inferred from light variations but never directly resolved. The spectra were ambiguous, showing dust and possible ices, but lacking a clean match to known solar system comets. To mainstream astronomers, these uncertainties were not red flags, they were expected. After all, interstellar objects are faint, distant, and fleeting. Data are always partial, always noisy, always incomplete. To alternative thinkers, however, the uncertainties provided fertile ground. If Oumuamua could be speculated upon as artificial, why not Atlas as well? Some asked whether Atlas could be a probe in disguise, an object designed to mimic a natural comet, hiding its true purpose in plain sight. Others wondered if it might be a fragment of something larger, a shard of an ancient structure, a piece of debris from a civilization's engineering project drifting across interstellar space like cosmic litter. The leap from faint spectral lines to alien probes may seem wide, and in truth it is. Yet the questions it raises are not entirely frivolous. If advanced civilizations exist, and if they send probes between stars, how would we recognize them? Would they gleam with obvious metallic surfaces, flashing unmistakable signals? Or would they blend into the cosmic background, camouflaged among the countless natural fragments drifting through the galaxy? Oumuamua taught us that strangeness alone can spark the debate. Atlas, while less dramatic, carries echoes of that lesson. Its irregularities may be natural, but they keep the door ajar for speculation. Each faint anomaly invites us to imagine scenarios beyond the ordinary. But there is also a lesson in caution. Oumuamua showed how easy it is for speculation to outpace evidence. For every theory of artificial sails, others proposed natural models. Frozen hydrogen sublimating invisibly, nitrogen ice chipped from a Pluto-like world, or fragile fractal dust aggregates. These ideas, while exotic, remained within the realm of natural physics. The debate highlighted a central truth. The boundary between the natural but unusual and the artificial is not always sharp. Incomplete data can make both possibilities seem plausible. Applied to Atlas, the lesson is sobering. While the artificial hypothesis stirs imagination, the balance of evidence leans toward the natural. The faint outgassing observed, the subtle coma, the chemical hints, all point to comet-like behavior. If Atlas is artificial, it hides itself with extraordinary care, leaving no trace beyond the vaguest whispers of anomaly. Yet the debate itself is valuable. By entertaining the artificial hypothesis, scientists sharpen the questions they ask. They refine models of outgassing. They develop methods for detecting faint accelerations. They consider what signatures would definitively distinguish natural from artificial. In this way, speculation, even if unproven, pushes science forward. The story of Atlas, then, is not only about what it is, but about how we interpret the unknown. To some, it is a comet-like visitor, fascinating but ordinary. To others, it is a candidate,
however slim, for something more, an emissary of intelligence, a fragment of technology, a silent probe moving through our skies. The tension between these views reflects a deeper human impulse. We want to know if we are alone. We want to believe that the universe might be populated not only by rocks and gas, but by minds and messages. When an object arrives from beyond the stars, it becomes a canvas for that desire. Whether we see a comet or a probe depends not only on the data, but on the lens through which we choose to look. And perhaps that is the greatest lesson from Oumuamua carried forward into the case of Atlas. We must remain open. Open to natural explanations, no matter how unusual. Open to artificial possibilities, no matter how controversial. Open to the reality that with only fragments of data, certainty is elusive. Atlas may not be a probe, it may not be artificial, but in the act of questioning, in the willingness to consider even the extraordinary, we prepare ourselves for the day when the evidence may be undeniable. The day when an interstellar visitor carries not only mystery, but unmistakable design. Until then, objects like Atlas will continue to hover in that gray zone, most likely natural, faintly anomalous, endlessly debated. They remind us that the frontier of discovery is not just about what we see in the telescope, but how we interpret it, how we weigh science against speculation, and how we confront the possibility that the universe might one day answer the question we have asked for so long. Are we alone?
For as long as humans have lifted their eyes to the night sky, they have seen more than stars. They have seen stories. A streak of light across the heavens was never just a fragment of rock burning in the atmosphere. It was a sign. A comet's glow was never merely sublimating ice. It was a portent. Ancient cultures across the world became interstellar storytellers, weaving the motions of celestial visitors into the language of gods, spirits, and destiny. The arrival of a comet, sudden and spectacular, often stirred both awe and fear. To the Babylonians, comets were the torches of heaven, blazing warnings of upheaval. Their astronomer priests carefully recorded appearances, linking them with the fates of kings and empires. The Chinese, with centuries of meticulous skywatching, catalogued comets and novae as guest stars, temporary visitors in the firmament, each carrying a symbolic message. Some foretold famine, others war, still others the death of emperors. To them, nothing in the sky was meaningless. Every visitor had purpose. Across the Mediterranean, the Greeks told stories of fiery-tailed stars as omens of disaster. Aristotle speculated on their natural origin, but still placed them in the sublunary realm of change and decay, a sign of the imperfect world. Later, in medieval Europe, comets became the hairy stars that heralded divine wrath. The Bayeux Tapestry depicts Halley's Comet blazing over the invasion of England in 1066, stitched into the fabric of history as a heavenly omen of conquest. In Mesoamerica, too, the heavens were a cosmic script. The Aztecs interpreted bright comets as signs that the order of the world was about to be shaken. Mayan astronomer priests wove the appearance of celestial travelers into their ritual calendars, blending astronomy with prophecy. To them, the sky was not a backdrop, but a living language, one that spoke in fire and motion. In every culture, celestial visitors were never neutral. They arrived carrying meaning, woven into myth and power, shaping how societies interpreted their place in the cosmos. The sky was the ultimate storyteller, and comets and meteors were its words. Fast forward to the modern era, and the language of the heavens has changed. Where ancient peoples saw omens, astronomers now see orbits. Where priests saw divine wrath, scientists see dust, ice, and gravity. The heavens no longer speak in symbols, but in equations. Yet even as we quantify the cosmos, the echoes of those old stories remain. Take 3i Atlas. To an astronomer, it is a faint point of light tracked across CCD detectors, a hyperbolic orbit plotted by software, a set of spectral lines hinting at dust and ice. It is data. But to the public imagination, it is more. It is a traveler from the stars, a messenger from beyond, a fleeting guest whose presence sparks questions larger than science alone can answer. The old instinct to tell stories has not vanished, it has simply shifted. In many ways, modern astronomy mirrors the mythic impulse of ancient cultures. Both seek to understand visitors from beyond the familiar. Both ask what it means that something strange appears in the sky. The difference lies in the tools. Myths wield metaphor, while astronomy wields measurement. Yet both are attempts to place human experience within a larger cosmic framework. Consider the parallels. The Babylonians read comets as warnings of political upheaval. Today, we see interstellar objects as signs of galactic processes, omens not of kings, but of planetary systems. A comet in ancient China might herald the death of an emperor. An interstellar object in modern science might herald the existence of countless unseen worlds ejecting debris into space. The language has changed, but the impulse to interpret remains. Even the names we give carry echoes of myth. Oumuamua, the first interstellar object, was named in Hawaiian, a scout, a messenger. 2I Borisov bore the name of its discoverer, but it too was called a wanderer, a traveler from another star. Atlas, the third, carries a name tied to the Greek Titan who held up the sky. The act of naming reveals the blend of science and story. These are not only catalog numbers, they're characters in a larger narrative of cosmic encounter. And like the myths of old, these modern encounters stir philosophical questions. Ancient cultures ask, what do the gods want of us, sending this fiery sign? Today we ask, what does the universe reveal of itself, sending this fragment across our skies? Ancient storytellers saw purpose in coincidence. Modern scientists see statistics. Yet both grapple with meaning in the unexpected. There is also a shared sense of rarity. To an ancient farmer, the sudden appearance of a comet was a once-in-a-lifetime event, unforgettable and awe-inspiring. To us, the detection of an interstellar object is just as rare, just as fleeting. Oumuamua in 2017, Borisov in 2019, Atlas shortly after. Each was a cosmic surprise, visible only briefly before vanishing forever. The scarcity fuels the sense of significance, just as it did thousands of years ago. And then there is fear. For ancient cultures, comets often symbolized danger, famine, plague, war. For us, interstellar objects provoke subtler fears. What if one struck Earth? What if their origins reveal violent processes in alien systems? What if the anomalies we detect suggest something beyond our comprehension? The fear may be different in form, but it springs from the same place. The recognition that visitors from the sky remind us of our vulnerability. Yet alongside fear lies wonder. Ancient peoples marveled at the beauty of the heavens, even as they trembled. Modern astronomy captures that same wonder in high-resolution images, in glowing spectra, in the sheer audacity of detecting a traveler from another star. To stand under the night sky, whether in Babylon 3,000 years ago or in Hawaii in 2019, is to feel the same awe. The heavens are alive, and they are speaking. In this sense, we are still interstellar storytellers. We no longer stitch comets into tapestries as omens of conquest, but we craft documentaries, news articles, and research papers that give them meaning. We no longer speak of the wrath of gods, but we speak of galactic history, planetary ejections, and the architecture of alien systems. Both are narratives, one mythic, one scientific. Both reflect the same desire to turn fleeting celestial visitors into enduring stories about ourselves. 3I Atlas, then, is part of a continuum. It joins the fiery omens of antiquity and the data-driven astronomy of today as chapters in humanity's long dialogue with the sky. When we ask whether it is just a visitor or a message, we echo the questions of our ancestors. They too asked whether the comet was simply a traveler or a sign sent with purpose. They too wrestled with coincidence and meaning. What has changed is not the instinct to interpret, but the framework in which interpretation occurs. We now understand that comets and interstellar objects are not agents of destiny, but fragments of cosmic evolution. Yet the very act of interpreting them as significant, whether scientifically or symbolically, remains deeply human. Perhaps this is the ultimate parallel. Both ancient myth and modern astronomy turn celestial visitors into bridges between the heavens and humanity, between the unknown and the known, between the silence of the cosmos and the stories we need to tell. In this way, Atlas is not only a data point, it is a chapter in the oldest story of all, our attempt to find meaning in the stars. And so the interstellar storyteller lives on. Once it was the shaman, the priest, the scribe. Today, it is the astronomer, the physicist, the science communicator. The tools have changed, but the role is the same. To look at the sky, to see a visitor, and to weave its presence into the story of who we are.
For as long as humanity has gazed upward, we have wondered, is the universe silent, or is it speaking to us? Each comet, each meteor shower, each flash of light has carried that question. And now, with objects like 3I/Atlas drifting in from interstellar space, the question sharpens once again. Could these natural phenomena be more than accidents of physics? Could they, in some sense, be messages? To the scientific eye, Atlas is the product of ejection events in distant star systems. A fragment torn free by gravitational instability, flung into interstellar night, wandering for eons until chance brought it across our path. But to the human imagination, the story can feel incomplete. For when something rare and extraordinary arrives from beyond the stars, it tempts us to see not just matter in motion, but meaning in motion. This is the heart of cosmic communication, the idea that the universe might speak through patterns, that within the flow of natural phenomena lies a deeper language, waiting to be understood. Patterns are, after all, how we make sense of the world. We see constellations in the scatter of stars. We trace cycles in the waxing and waning of the moon. We find rhythms in the rise of the sun, the seasons, the tides. To live on Earth has always meant listening to patterns written across the sky. Some of those patterns guide survival, when to plant, when to harvest, when storms approach. Others inspire philosophy and myth. All are attempts to read the universe as if it were speaking directly to us. The question is whether that instinct is purely human projection, or whether there is indeed communication woven into the fabric of the cosmos. Consider pulsars. When they were first discovered in the 1960s, astronomers noted the regularity of their signals, precise bursts of radio waves, arriving like the ticking of a clock. They were so consistent, so unlike any natural source then known, that the first detection was nicknamed LGM-1, Little Green Men 1. The idea that pulsars might be signals from extraterrestrials was seriously entertained, however briefly, before natural explanations prevailed. We now know pulsars are rapidly rotating neutron stars, their beams sweeping across space like cosmic lighthouses. But that initial moment reveals something important. When confronted with patterns of astonishing regularity, our first instinct was to wonder if the universe was speaking. Or take the cosmic microwave background, the faint afterglow of the Big Bang. It is not random noise, but a pattern imprinted with the story of the universe's earliest moments. By decoding its fluctuations, scientists have read a message from nearly 14 billion years ago.
one that tells us of density variations, primordial ripples, and the seeds of galaxies. The universe did not intend to send this message, and yet it speaks all the same. It speaks of origins. In this light, Atlas and its interstellar kin can be seen as part of the same phenomenon, carriers of cosmic information. Not messages in the deliberate sense, but messages in the structural sense. Each fragment that drifts into our solar system is a letter torn from a larger book, the book of planetary systems forming and dying across the galaxy. By studying its composition, its trajectory, its speed, we decipher a story about distant worlds we cannot yet see. The universe communicates through these travelers, even if it does not choose to do so. But some thinkers go further. They ask, what if the universe itself has an intelligence of sorts? What if patterns are not just side effects of physics, but intentional expressions, ways in which the cosmos ensures its story is heard? This is not mainstream science, but it is a philosophical speculation that lingers. For if we ourselves are products of the universe, minds born of stars and atoms, then perhaps the act of finding meaning in cosmic patterns is not separate from the universe's nature, but an extension of it. Through us, the universe may be communicating with itself. This raises a provocative perspective on objects like 3I/Atlas. What if such visitors are not random? What if their rarity, their timing, their anomalies are not only statistical accidents, but signals woven into the flow of cosmic history, not deliberate in the way a radio broadcast is deliberate, but meaningful in the way poetry emerges from chance associations of words? Think of it this way. A comet that arrives at a crucial turning point in human history may inspire myths that shape civilizations. An interstellar object arriving just as our species develops the tools to detect it may inspire scientific revolutions. In both cases, the event becomes part of the conversation between cosmos and consciousness. Of course, the scientific mind warns against anthropomorphism. The universe is vast, indifferent, governed by laws that operate without intention. To claim that natural phenomena are messages risks collapsing into superstition, but to ignore the communicative power of patterns risks missing something profound. Communication need not require intention, it requires only transmission and reception. If the universe transmits patterns, and if we are capable of receiving and interpreting them, then communication, of a sort, exists. The challenge then is discernment. How do we distinguish between noise and signal, between coincidence and communication? The Chinese astronomers who tracked guest stars thousands of years ago believed each arrival carried meaning. Modern astronomers, with their telescopes and computers, also believe arrivals like Atlas carry meaning, though of a different kind, meaning about astrophysics, chemistry, galactic dynamics. The continuity is striking. Both ancient and modern minds see the sky not as mute, but eloquent, a place where stories are told through light and motion. In that sense, Atlas becomes part of a larger cosmic dialogue. It speaks of violence in alien systems, the gravitational slingshots that expelled it. It whispers of its composition, telling us about the materials that built distant planets. It demonstrates the permeability of the interstellar void, reminding us that our solar system is not an island, but a node in a galactic sea of exchange. Every detail we extract is a piece of a message, one that expands our sense of context. But there is another layer, more subtle, more human. When we ask whether Atlas is a visitor or a message, we are also asking about ourselves. For meaning is not only in the object, it is in the interpreter. If we choose to see a message, then in a sense there is one. The universe becomes a mirror, reflecting back the stories we are ready to tell. This does not diminish the science. On the contrary, it deepens it. To study interstellar objects is to participate in a conversation that stretches across time and space. We gather data, we build models, we test hypotheses, but beneath it all lies the recognition that we are listening for patterns, listening for the universe to speak. Perhaps one day the communication will be unmistakable, a signal from an intelligence beyond our own, woven into radio waves or carried on a probe. But even if that day never comes, the universe is already speaking, constantly, endlessly, through the phenomena we observe. The question is not whether it communicates, but how we choose to hear. 3i/Atlas is one such voice in that cosmic chorus, a faint visitor, here and gone in the blink of cosmic time, yet bearing messages older than humanity itself. To see it is to glimpse a pattern unfolding across the galaxy. To study it is to translate a fragment of the universe's language. And to wonder about it is to admit that we too are storytellers in a dialogue far larger than ourselves.
For most of human history, the arrival of a strange object in the sky was interpreted with the naked eye and the human imagination. Today, the imagination remains, but it is guided, refined, and expanded by technology. If interstellar visitors like 3i/Atlas are messengers, then telescopes, sensors, and algorithms are the translators, turning faint signals into stories we can understand. When astronomers first noticed Atlas in 2019, it was not because someone happened to glance up at the sky on a dark night. It was because a global web of telescopes, cameras, and data pipelines was already watching. The Atlas Survey, Asteroid Terrestrial Impact Last Alert System, was designed not to find interstellar travelers, but to detect near-Earth objects that could threaten our planet. Every clear night, its twin telescopes in Hawaii scan the heavens, capturing rapid images of the same patches of sky. Software then compares those images, looking for the telltale motion of a dot that shifts against the background of stars. This is how 3i/Atlas was first flagged, as a moving speck, faint but persistent, its path inconsistent with ordinary solar system orbits. Within hours, the data spread across global networks, alerting other observatories to track and confirm. What once would have been a mystery glimpsed by a handful of skywatchers is now the beginning of a planetary collaboration. Modern telescopes play a crucial role in this decoding. Wide-field survey telescopes like Pan-STARRS and Atlas sweep vast regions of the sky, ensuring that transient phenomena are not missed. Precision instruments like the Very Large Telescope in Chile or the Keck Observatory in Hawaii then zoom in, gathering spectra, light broken into its component wavelengths, the fingerprints of chemical composition. Space-based observatories, free from the distortion of Earth's atmosphere, provide complementary data. Together, they weave a multidimensional picture out of a visitor that, to the naked eye, would appear as nothing more than a faint smudge. But telescopes alone are not enough. The universe floods us with data. Every night, surveys collect terabytes of images filled with stars, galaxies, asteroids, satellites, and noise. To find an interstellar object within that torrent requires more than human eyesight. It requires algorithms, tools that can sift, filter, and detect anomalies at scales the human mind cannot manage. Here is where artificial intelligence has begun to reshape astronomy. Machine learning models are trained to recognize patterns, the steady trails of asteroids, the flicker of variable stars, the subtle signatures of transients. They can flag unusual motion, detect faint comas, or even predict the likely origin of an object's trajectory. In the case of Atlas, while traditional image differencing identified its movement, AI-driven pipelines are increasingly becoming the guardians of the unexpected. Without them, we risk drowning in data, blind to the rare visitors hidden within. AI also helps in decoding composition. Spectral data is notoriously complex,
absorption lines blending, noise obscuring clarity. Machine learning can compare observed spectra against vast databases, teasing out faint signals of water ice, carbon compounds, or metallic elements. What once required painstaking manual analysis can now be accelerated, revealing insights in days rather than months. Even beyond detection and analysis, technology shapes how we reconstruct interstellar journeys. Orbital simulations, powered by supercomputers, take an object's observed path and rewind it across time. For Atlas, this means tracing its hyperbolic trajectory back through space, searching for possible origins. Was it ejected from a young star system? Flung by a gravitational dance with giant planets? Simulations can test millions of scenarios, narrowing possibilities until we glimpse the birthplace of a traveler that left its home millions of years ago. And yet, as powerful as telescopes and AI are, they also highlight the fragility of evidence. Interstellar objects are fleeting. They appear suddenly, stay briefly, and then vanish forever into the dark. Every photon we capture, every data point we store, becomes precious. Technology allows us to stretch the faint signal, to wring meaning from scarcity. Without these tools, Atlas would have tossed unnoticed, its story untold. The role of technology is not just in the science, but also in the storytelling. Data becomes images, spectra become colors, orbits become animations. Through visualization, the abstract is made tangible. We can watch the arc of Atlas across the solar system, its trajectory plunging in and out, hyperbolic and free. We can see simulations of its possible shape, elongated, comet-like, fragmentary. Technology translates numbers into experiences, allowing not just astronomers, but the wider public to witness the visitor. There is also a democratic dimension. Astronomy has become more open, more global because of digital networks. The discovery of Atlas was not confined to Hawaii. It was broadcast, shared, confirmed by telescopes across continents. Amateur astronomers contributed, adding data from backyard telescopes that linked into professional archives. Online platforms allow anyone to download orbital data, to simulate Atlas's path on their own computer. In this way, technology transforms interstellar objects into global phenomena, shared stories rather than hidden curiosities. And yet, for all its power, technology does not dissolve mystery. The best telescope still cannot resolve an interstellar object's shape directly. It remains inferred from variations in brightness. Spectral data still leaves ambiguity about composition. AI can highlight patterns but not assign ultimate meaning. In other words, our tools extend our reach, but they do not grant omniscience. The decoding remains partial, the message incomplete. This tension is essential. Technology is both a lens and a limitation. It lets us see further, faster, more precisely, but always within boundaries. Atlas reminds us of this. Despite global networks, supercomputers, and AI, what we truly know about it fits into a narrow band. A trajectory, a rough brightness profile, faint chemical hints. The rest is interpretation, imagination, speculation. Still, one cannot help but marvel at the progress. Imagine explaining to an ancient skywatcher that today, when a faint dot appears, telescopes on Earth and in orbit immediately capture its light. That computers analyze its spectrum, revealing atoms forged in distant suns. That algorithms trace its path back through millions of years, mapping the architecture of unseen systems. To that skywatcher, such tools would seem like magic, but to us, they are the instruments of listening to visitors like Atlas, decoding the faint whispers of the interstellar medium. Technology, then, is not just passive instrumentation, it is active translation. Without Atlas, it would be invisible. With it, Atlas becomes a narrative, an object with a history, a composition, a role in the galactic story. Each improvement in detection, each advance in AI sharpens the conversation. We move from silence to signal, from ignorance to insight.
And perhaps most profoundly, technology ensures continuity. Ancient cultures could only tell stories of the objects they saw in their lifetimes. We, with our telescopes and data archives, can preserve the story of Atlas forever. Its light is gone, but its data remains, encoded in digital form, accessible to future generations. Technology turns fleeting visitors into permanent voices in the cosmic dialogue. So when we speak of decoding interstellar objects, we are not speaking metaphorically. We are describing the literal process by which photons from across the galaxy are transformed into meaning. Telescopes gather the raw symbols, AI parses the syntax, simulations reconstruct the grammar. What emerges is a message, not written in words, but in light, motion, and chemistry. Technology is our interpreter, teaching us to hear the language of the universe.
When 3II/Atlas was confirmed as an interstellar object, it was already slipping away, another fleeting guest vanishing into the dark. But instead of leaving us only with questions, it left us with a challenge, to be ready for the next one. For if Atlas taught us anything, it is that interstellar visitors are not once-in-a-millennium events. They're more common than we once believed. The universe is throwing open its doors, and the question is whether we will be prepared to welcome what comes through. For centuries, we suspected that fragments from other star systems must pass through our neighborhood from time to time. After all, our own solar system ejects comets into interstellar space when giant planets hurl them outward. If this process happens here, it must happen everywhere. But without the right tools, such visitors were invisible, lost in the vast background of stars and the faint clutter of our own cometary debris. It was only in 2017, with the detection of Oumuamua, that the first confirmed interstellar object was identified. Just 2 years later, Borisov arrived, and then Atlas soon after. 3 in just a handful of years shattered the notion of rarity. Suddenly, astronomers began to ask not if more would come, but how many we should expect. The answer lies in surveys. Vast, systematic scans of the sky designed not just to hunt for the obvious, but to catch the fleeting, the unusual, the extraordinary. Until now, interstellar discoveries have been lucky accidents. Oumuamua was spouted by Pan-STARRS, a survey originally tasked with tracking asteroids. Borisov was found by an amateur astronomer with a keen eye and persistence. Atlas was caught by a system designed to guard Earth from asteroid impacts. None of these were built specifically to find interstellar travelers, and yet they did. Which raises an exhilarating thought. If accidental discovery has already revealed 3, how many more will we find when we search deliberately? The key to this future is the Vera C. Rubin Observatory, scheduled to begin full operations in the near future. Located in Chile, its flagship project, the Legacy Survey of Space and Time, will scan the entire southern sky every few nights with unprecedented depth and speed. Its 8.4-meter mirror and massive camera will capture 20 terabytes of images each night, creating the most detailed time-lapse of the universe ever assembled. Among the billions of stars and galaxies, it will track the motions of countless small objects, including those with hyperbolic trajectories, the unmistakable signature of interstellar origin. Astronomers predict that once Rubin begins its survey, we may detect dozens of interstellar objects every year. Some will be small, faint, and barely trackable. Others may be larger, brighter, offering rich opportunities for study. The pipeline of discovery will shift from chance to certainty. We will not just marvel at isolated stories. We will build the first census of interstellar visitors. This shift has profound implications. Each object is a sample from another star system, a fragment carrying chemical and structural information about worlds we cannot see directly. If Rubin detects dozens or even hundreds of such objects in the coming decades, we will hold in our data the beginnings of a galactic archive. We will know what distant comets are made of. We will compare the ices of one system with the dust of another. We will map not just our solar system, but the diversity of planetary systems across the Milky Way. And technology will not stop with Rubin. The Nancy Grace Roman Space Telescope, launching later this decade, will expand our ability to detect faint moving objects from orbit, free of atmospheric distortion. Radio telescopes may be tuned to listen for subtle outgassing or unusual emissions. Infrared space observatories will catch the faint heat signatures of objects too dark to reflect much sunlight. The synergy of ground-based and space-based instruments will transform interstellar detection from a rare spectacle into a routine science. Artificial intelligence will sharpen this revolution. With billions of detections each night, human eyes cannot possibly identify every anomaly. AI models trained on simulations of interstellar trajectories will flag hyperbolic candidates in real time. Automated alerts will ripple across the globe, summoning telescopes to observe before the visitor slips away. What took weeks of verification for Oumuamua may in the near future happen in hours. We are building not just the capacity to detect, but the reflexes to respond. Response, after all, is the next frontier. Detection is only the first step. The real prize is proximity, getting close enough to touch, sample, or even follow an interstellar visitor. Several mission concepts have already been proposed. The European Space Agency and NASA have considered interceptor spacecraft, probes kept in readiness, capable of launching quickly to chase down a newly discovered interstellar object. The challenge is enormous. These objects travel at tens of kilometers per second, on paths that give little warning before they depart. But the payoff is equally enormous. To analyze one up close would be to hold in our hands a fragment of another star system, a material message delivered across light years. Future surveys make such missions plausible. If we know that interstellar objects will appear regularly, we can prepare accordingly. We can station spacecraft at vantage points, waiting for alerts. We can design engines capable of rapid acceleration, intercepting an object before it vanishes. Some even dream of sample return missions, scooping dust from a visitor's coma and bringing it back to Earth, a piece of another world studied in our laboratories. The discovery of Atlas and its companions has therefore sparked not only curiosity, but planning. Astronomers now speak openly of a new era, an age of interstellar object science. Just as exoplanet discovery shifted from rare outliers to thousands cataloged, so too may interstellar detections multiply. And with each new visitor, the questions will deepen. How many systems eject icy comets? How many eject rocky fragments? What clues do their compositions give about habitability, about the ingredients of life, about the universality of planetary processes? There is another layer to this preparation, the philosophical one. As more interstellar visitors arrive, humanity will face them not with the shock of rarity, but with the patience of study. They will become part of our intellectual landscape, no longer omens of myth, but data points in a cosmic survey. And yet their mystique will remain. Each will still be a messenger from beyond, a traveler carrying secrets older than our civilization. Each will still invite us to wonder, is this mere debris, or could some fragment, someday, be more? In this sense, preparing for more visitors is not only about technology and missions, it is about preparing ourselves, scientifically, culturally, imaginatively. The sky will no longer be silent in its intervals between visitors. It will be alive with motion, with arrivals and departures, with stories written in trajectories and spectra. Humanity will become accustomed to the idea that we are not isolated. The galaxy leaves traces at our doorstep. We must learn how to read them. Already, some astronomers speculate that in the coming decades we may detect thousands of interstellar objects, ranging from kilometer-wide comets to tiny fragments barely visible. Among them may be icy relics, rocky shards, or even bodies unlike anything in our solar system. The diversity may surprise us.
Patterns may emerge, perhaps comets with unusual chemistry, perhaps distributions that hint at the architectures of alien systems. With enough data, we may even reconstruct the galactic processes that govern how planets form, how systems evolve, how debris drifts between the stars. All of this begins with preparation, with surveys like Rubin, with AI pipelines, with mission concepts waiting for their target. Oumuamua showed us the first glimpse. Borisov proved that interstellar comets exist. Atlas reminded us that such discoveries are not one-offs, but part of a pattern. The next step is to be ready, so that when the next traveler arrives, we are not merely watching it fade, but seizing the opportunity it brings. The future, then, is not waiting passively, but listening actively. The sky will deliver visitors. Our task is to be ready, to detect, to decode, to pursue. Each new object is a question from the galaxy, and we, with our telescopes, algorithms, and spacecraft, are preparing to answer.
When 3I/Atlas streaked into the solar system, it was more than a curiosity. It was more than a comet-like blur fading into the void. It was, in essence, a fragment of another world, an interstellar time capsule, carrying in its dust and ice the memory of a system not our own. For scientists, this was not just an object to catalog. It was a rare chance to glimpse processes billions of years and light years away, preserved in miniature form. It was a teacher, however fleeting, and the lessons it left behind continued to reshape our understanding of planetary formation. The first lesson of Atlas is one of universality. Until Oumuamua in 2017, interstellar objects were theories, abstractions scribbled into models of how planetary systems evolve. We knew that as young systems form, gravity is messy and often violent. Giant planets jostle smaller bodies, flinging comets and asteroids outward. Many escape entirely, cast adrift into interstellar space. Theoretically, the galaxy should be full of such debris. Yet theory alone is never enough. Oumuamua gave us the first proof. Borisov gave us the second. Atlas gave us the third. Together, they tell us that ejection is not rare, but common. That planetary systems across the Milky Way bleed fragments into the galactic sea. This matters because it links our solar system to the wider galaxy. The icy comets of our Oort cloud are not unique. They are part of a galactic pattern. The asteroid belts around other stars, though unseen, likely follow similar dynamics. Atlas is a confirmation that we are not exceptional, that what happened here is happening everywhere. Planetary formation is not an isolated story, but a cosmic chorus, with billions of systems writing variations on the same theme. The second lesson lies in composition. By studying the light of Atlas as it reflected and refracted through dust, astronomers glimpsed its material makeup. Though faint and ambiguous, the spectra suggested volatile ices and dusty grains, resembling the comets of our own system. That similarity is profound. It means that the chemistry of distant systems is not wholly alien, but familiar. The building blocks we find here, water ice, carbon compounds, silicates, may be common across the galaxy. If true, then the conditions that led to life on Earth are not a cosmic accident. They are written into the chemistry of the stars. Yet Atlas also hints at diversity. Some data suggested unusual brightness variations, irregular outgassing, perhaps even structural fragility. If Atlas was a loosely bound fragment, a fragile shard, it could speak of a different history than our comets. Perhaps its home system formed under harsher conditions.
Perhaps its parent body was shattered by collisions or baked by radiation before being ejected. Each anomaly is a clue, a whisper of environments we cannot see directly. The third lesson is dynamical. By reconstructing its trajectory, astronomers learned not only where it came from, but how such objects travel. Its hyperbolic path confirmed that it was not bound to the sun. It was passing through, never to return. Its speed, higher than typical solar comets, matched predictions of ejection velocities from planetary systems. In this way, Atlas was not just a visitor, but a data point in galactic dynamics. Each interstellar object helps refine our understanding of how systems form, scatter, and evolve. Each trajectory is a line on a larger map, the invisible network of paths connecting stars through the exchange of debris. Taken together, these lessons give us something extraordinary, glimpses into other solar systems without ever leaving our own. When we study Atlas, we are studying the geology and chemistry of a place we cannot see. We are holding a fragment of an alien world in our equations, our simulations, our spectra. It is as if a message in a bottle had washed ashore from an unseen continent, carrying the soil and scent of a distant land. This is why astronomers are so captivated by interstellar objects. They are the only physical samples we have so far from beyond our sun. Meteorites that fall to Earth tell us about the asteroid belt. Comet dust collected by spacecraft tells us about our Oort cloud. But interstellar objects are something else entirely. They are emissaries of the unknown, carrying the materials of systems light years away. Each one expands the boundaries of our laboratory to galactic scales. Atlas also teaches us about humility. For all our telescopes, our computers, our theories, the data we gathered was incomplete. It was faint, noisy, fragmentary. We could not pin down its exact shape. We could not resolve its structure directly. We could not track it indefinitely. It slipped away, leaving behind more questions than answers. And yet, in those unanswered questions lies the essence of discovery. Science is not the act of knowing everything, but of learning just enough to ask better questions next time. Atlas forced us to sharpen our tools, refine our models, and prepare for the next encounter. Perhaps the most profound lesson of Atlas is existential. To see a fragment of another world drift through our skies is to realize that we are part of something larger. Planetary systems are not sealed bubbles, isolated and separate. They are porous, exchanging matter across the gulfs of space. What leaves one star may, after eons, pass another. In this sense, Atlas is not just a visitor. It is a thread in the galactic web that links all worlds. It is evidence that the story of Earth is not written in isolation, but in dialogue with the broader cosmos. Some even speculate about the role of such objects in the origins of life. Could fragments like Atlas carry organic molecules between systems? Could panspermia, life spreading across the galaxy on the backs of comets and asteroids, be more than a hypothesis? While we have no evidence that Atlas carried anything biological, the possibility lingers. Its icy dust could, in principle, protect complex molecules over interstellar journeys. If so, then objects like Atlas are not just lessons in planetary formation, but in the potential continuity of life itself. And finally, Atlas teaches us about timing. It arrived at a moment when our species had the instruments to notice it, the networks to track it, the models to interpret it. A century earlier, it would have passed unseen. A century later, we may already have spacecraft waiting to intercept such visitors. That it came now, when we are just learning to look outward with precision, feels symbolic, even if coincidence. It reminds us that discovery is not only about the object, but about our readiness to see it. So what, then, does 3I/Atlas teach us? It teaches us that planetary formation is universal, that chemistry is shared across the galaxy, that trajectories carry stories of violence and scattering, that fragments can survive eons to deliver their tales to distant stars. It teaches us humility in the face of incomplete data, but also wonder at the glimpse of worlds beyond our reach. It teaches us that we are part of a galactic community of systems, bound not only by light, but by matter exchanged across the void. And perhaps most importantly, it teaches us that every visitor, no matter how faint or fleeting, is a teacher. If we listen carefully, if we decode patiently, we can learn not only about distant systems, but about ourselves, our curiosity, our place, our connection to the vast story unfolding among the stars.
When 3I Atlas drifted across the solar system, its significance was not only scientific. Numbers, spectra, and orbital mechanics could only tell part of its story. The other part, the part that lingered in the imagination, was what it said to us not as a data set, but as a messenger. For every telescope pointed its way, there was also a human being behind the lens, gazing upward and wondering, what does this mean for us? To some, Atlas was a silent reminder of smallness. Its journey began in a star system unimaginably far away. It crossed interstellar distances for millions, perhaps billions of years before brushing past our sun. And then, in a brief encounter spanning only months, it appeared in our skies, flickered in our instruments, and vanished again into the black. Against such scales of space and time, human lifetimes shrink into insignificance. Civilizations rise and fall while an interstellar fragment glides between the stars. For all our technologies and ambitions, Atlas reminds us that we are but a fleeting moment in a cosmic story so vast it defies comprehension. And yet that very smallness can also be seen as a gift, for in recognizing our scale we also recognize our place. The universe is not arranged around us. We are participants, not masters. To see Atlas moving silently through space is to feel the weight of humility, a humility that cuts through our illusions of control. It tells us, you are not the center. You are part of something larger. At the same time, Atlas carries another message, not one of insignificance, but of connection. Here was a fragment from another world, passing close enough for us to notice, to measure, to wonder about. In the vast emptiness of the galaxy, the odds of such encounters being visible to a young species like ours might seem impossibly small. Yet here it was. Its appearance whispered of a hidden fabric, an interwoven web where star systems exchange not only light, but matter. What happens around distant suns eventually touches us, just as what happens here may one day drift to other stars. Atlas reminds us that the boundaries we imagine between systems are porous. We're not isolated islands, but threads in a galactic tapestry. This realization bends toward philosophy. For if fragments can travel between worlds, if debris can cross light years and survive to reach us, then so can stories, metaphors, and meanings. Atlas becomes not only an object of study, but a mirror in which we see ourselves. Its path across our sky can be read as coincidence or as metaphor. A traveler arrives, lingers briefly, leaves without explanation. That story feels achingly familiar because it is the story of our own lives, We are all temporary visitors passing through the cosmos, illuminated briefly before fading back into silence. To some, this makes Atlas a kind of cosmic poem. Its trajectory is a verse written not in words, but in motion. Its silence is part of its message. It does not explain itself, and yet in not explaining, it speaks volumes about impermanence, about transience, about the fleeting beauty of encounters. If there is symbolism in its appearance, it is that the universe is vast, mysterious, and filled with wonders that we cannot hold forever. The value lies not in possession, but in the brief moment of recognition. There is another message, too, one about responsibility. In the face of such vastness, it might be tempting to retreat into insignificance, to declare that nothing we do matters. But Atlas says the opposite. For while we are small, we are also uniquely capable of awareness. Out of all the species on Earth, and perhaps far beyond, we are the ones that noticed. We are the ones who measured, who asked, who debated. Our smallness does not diminish us, it sharpens the preciousness of our consciousness. In all the billions of years Atlas traveled, it may have passed countless suns, countless planets, countless barren rocks. And yet it was here, with us, that it became a story, an object of meaning. That is not nothing, that is extraordinary. The message, then, is that awareness carries responsibility. If we are capable of seeing ourselves as small, we are also capable of choosing to live with humility, with stewardship, with wonder. To look at Atlas is to realize that Earth itself is fragile, a finite home moving through a boundless dark. Its thin atmosphere, its delicate biosphere are as vulnerable as the cometary dust we tracked across the void. To ignore that lesson would be to miss the very point of the encounter. There is, too, the message of continuity. Atlas was the third interstellar object discovered. It followed Oumuamua and Borisov, and it will not be the last. These visitors remind us that discovery is not a one-time event, but part of an unfolding dialogue with the cosmos. Each one extends the conversation, pushes the boundary of what we know. Their cumulative message is simple. Keep looking, keep listening. The universe is not silent. It speaks in fragments, in travelers, in fleeting glimmers, but only if we are watching. For some, the appearance of Atlas invites speculation. Could such objects ever be intentional messengers, probes, or signals from other intelligences? Science cautions restraint, pointing to natural explanations first, but even in the absence of evidence for intention, the metaphor remains. Whether designed or accidental, whether probe or pebble, Atlas still speaks. Its very existence is a communication of sorts. It tells us that the processes that shaped us are not unique, that other systems, other worlds, other chemistries exist. It reminds us that the galaxy is not empty, but alive with motion and exchange. If one were to translate its message into words, perhaps it would say, "You are not alone." Not in the sense of other civilizations, although they may exist, but in the sense of being part of a greater whole. Your solar system is one among billions. Your planet is one among countless worlds. You are connected, even if only by fragments drifting through the night. And perhaps its message contains a warning, too. Objects like Atlas travel fast. Their paths are unpredictable. Some may one day cross closer to Earth, even posing danger. The same universe that delivers fragments of wonder can also deliver threats. To heed the message is to take seriously our responsibility to understand, to prepare, to guard our fragile world against what the cosmos may send. Wonder and vigilance are not opposites, they are partners in survival. Atlas also teaches us about perspective in time. Its voyage lasted far longer than human history.
while empires rose and fell, while languages evolved and vanished, while entire civilizations flourished and collapsed, it continued unceasingly, a silent traveler in the dark. To recognize this is to recognize the brevity of our moment, but also the potential of our legacy. What will humanity be when the next interstellar visitor arrives? What stories will we have written? What knowledge will we have gained? What care will we have shown for our fragile planet? Atlas reminds us that the universe will continue, with or without us. The choice is whether we will write ourselves into its ongoing story or let ourselves fade, unnoticed, into silence. Ultimately, the message of 3i Atlas is layered. It is humility in the face of immensity. It is wonder at connection across light years. It is responsibility born of awareness. It is the reminder that impermanence gives meaning, not despair. It is the invitation to keep looking outward, to let discovery shape not only our science, but our sense of self. We may never know the exact star it came from, nor the precise conditions of its birth. We may never hold its dust in our hands, nor read in detail the record written in its ice. But we do not need certainty for meaning. The message was never about answers. It was about perspective. A traveler from afar passed through, and in that brief encounter, it reminded us of our place in the vastness. Small? Yes. Fleeting? Yes. But also aware, connected, and capable of wonder. That, perhaps, is enough.
As 3i/ATLS disappears into the dark, the question remains, was it merely a visitor? A fragment of a distant system passing through our solar neighborhood? Or was it something more? A message, subtle and silent, conveyed across the vastness of space. For months, humanity tracked its motion, analyzed its light, deciphered its faint spectral signatures. And yet, despite all our tools, all our telescopes, all our calculations, the question lingers. It is not a question with an easy answer, and perhaps it is the nature of the question itself that carries the most meaning. Let us consider it as a visitor first. In this view, Atlas is a cosmic traveler, cast adrift by the gravitational chaos of a star system we may never see. Its trajectory is a product of forces impersonal and immense, a hyperbolic path that intersects our solar system only by chance. Its speed, its composition, its fleeting presence are all evidence of this randomness. It is a messenger only in the sense that it carries information embedded in its matter, the chemical fingerprint of a star and planets long ago and far away. In this sense, it is a teacher, not a communicator. Its lessons are about the mechanics of planetary formation, the dynamics of ejection, and the universality of matter across the galaxy. It reminds us of the processes that shape worlds, of the patterns that govern cosmic debris, and of our ability to decipher these patterns using science. Yet, even framed purely as a visitor, there is wonder. It traveled across light years, journeyed through the void for millions of years, and arrived within the reach of human instruments at a moment when we were ready to see it. This rarity, this serendipity, imbues the encounter with significance beyond mere numbers. To witness such a visitor is to feel the immensity of time and space pressing against our consciousness, to glimpse the vastness of the galaxy, and to realize that the universe continues to move, indifferent to us, yet capable of intersecting with us in moments of revelation. Now, consider it as a message. Here, Atlas transforms from a passive traveler into an active participant in a conversation that stretches across the galaxy. Perhaps it is not a message in words or intention, but a message in the form of a presence, a reminder that we are not isolated. Its passage across the solar system is a narrative, a fragment born elsewhere, ejected by unseen forces, arriving at a place that, for a brief time, can observe it. That narrative becomes a reflection of existence itself, a statement about connection, about cosmic context, about the intricate web of interactions that link star systems across unimaginable distances. As a message, Atlas speaks in multiple languages. Its trajectory tells of physics, the balance of gravity and momentum, the ejection mechanisms of distant planetary systems. Its composition speaks of chemistry, the building blocks that may be common throughout the Milky Way. Its fleeting appearance speaks of time and scale, the brevity of human life compared to cosmic journeys, the patience required to understand a universe measured in millions of years. In this sense, the message is both humbling and elevating. It tells us of our smallness, yet also of our capacity to perceive, to decode, and to place ourselves within the broader story of the galaxy. Whether visitor or message, the encounter forces reflection. It forces us to ask not only about the object itself, but about ourselves. How do we interpret the rare and the extraordinary? How do we respond to phenomena that stretch the imagination and defy the boundaries of our knowledge? How do we integrate fleeting moments of revelation into the ongoing human story? These are not questions about comets or asteroids. They are questions about perception, about curiosity, about the willingness to embrace mystery without fully resolving it. Indeed, perhaps the most profound lesson lies precisely in ambiguity. Atlas does not reveal all of its secrets. Its structure is inferred, not resolved. Its composition is partially known but uncertain. Its origin is hypothesized but unconfirmed. And this uncertainty is itself a form of communication. The universe, in presenting us with such an enigmatic visitor, invites us to explore, to measure, to calculate, and ultimately to imagine. It challenges us to expand our tools, to refine our models, and to cultivate patience in the face of vast unknowns. In this way, ambiguity becomes the medium through which wonder is transmitted. Atlas is also a reminder that discovery is not instantaneous. It is cumulative, layered, and collaborative. From the initial detection by the Atlas telescopes to the follow-up observations by observatories around the world, every data point contributed to the emerging understanding. Every observation, every spectrum, every simulation added texture to the story. The visitor or message is not contained in a single moment, but emerges through the collective efforts of a global community. In this sense, Atlas is also a reflection of human curiosity, our desire to reach outward, to map, to quantify, and yet never to dominate. Its story is a bridge between eras and perspectives. In ancient times, celestial visitors were omens, comets and meteors interpreted as warnings or portents. In modern times, they are objects of science, carriers of empirical information. Yet in both cases, they inspire the same human response: awe. Atlas reminds us that the urge to interpret, to find meaning, is not a weakness, but a defining trait. We are by nature seekers of patterns, readers of the sky, listeners to the faint whispers of the cosmos. The visitor or message may be indifferent, but we are not. Our attention, our analysis, our wonder are the forces that translate fleeting cosmic events into human significance. Perhaps the central beauty of Atlas lies in its duality. It is both visitor and message, material and metaphor, empirical and symbolic. To insist on one interpretation alone is to miss the richness of the encounter. Its physical presence teaches us about physics and chemistry, while its existence, fleeting and mysterious, teaches us about perspective and humility.
Its trajectory reminds us that the universe operates on scales far beyond our own, while its visibility reminds us that we are capable of noticing, of understanding, and of reflecting. In this interplay, Atlas becomes not merely a comet or a rock, but a catalyst for thought, a spark for imagination, and a prompt for philosophy. The implications extend beyond astronomy. When we consider the visitor or message, we are also considering our place in the cosmos. Earth, vibrant yet fragile, is a small rock orbiting an ordinary star. Our solar system is but one among billions. The Milky Way itself is only one galaxy among countless others. In this vastness, a single fragment traveling across interstellar space offers perspective. That life, intelligence, and curiosity may be rare, but they are possible. That the galaxy is not static, but dynamic, constantly exchanging matter and energy. That the very act of noticing is a form of participation in a cosmic dialogue. In the end, the question of visitor or message may be unanswerable. Perhaps it is meant to be. Perhaps the true value lies not in resolution, but in engagement. Atlas challenges us to look upward, to track the faint traces of interstellar wanderers, to analyze, to imagine, to wonder. It reminds us that even in a universe indifferent to our existence, there is beauty, complexity, and connection. That is a message of its own. So as Atlas vanishes into the void, leaving behind only observations, equations, and speculation, we are left with more than data. We are left with curiosity. We are left with the reminder that the universe is immense, unpredictable, and alive with phenomena that can ignite imagination and inquiry alike. We are left with the sense that, whether visitor or message, each interstellar object is a call to wonder, a nudge to question, a prompt to explore. Perhaps that is the ultimate takeaway. Atlas does not need to answer our questions. Its passage, however brief, suffices to provoke them. Its silence is an invitation to listen. Its trajectory is a prompt to follow. Its composition, however faintly known, is a lesson in universality and diversity. And its very existence, a lone traveler crossing the galaxy, reminds us that the cosmos is vast,